হ্যাঁ স্যার। হ্যালো। হ্যাঁ হ্যাঁ, লাইভ করছি, এই যে করে দিয়েছি। হ্যাঁ, ওইটাই দেখছি স্যার, দেখাচ্ছে নাকি। লাইভ তো করে দিলাম। ওবিএসটা নিচ্ছে না নাকি? আচ্ছা স্যার, আমি দেখছি। হ্যাঁ, হ্যাঁ হ্যাঁ, জানিয়ে দিচ্ছি।
So welcome all participants and viewers. So if you like to check your presentation, you are requested to share your screen one by one maybe, so that you can see whether your slides are being shown properly or not. So maybe Dr. Shubhnarayan Singh may start. Uh, there is a one. Yes, we can see your slides. Thank you. So maybe Dr. Piyush Poshak may try.
Okay,
There is a box with an arrow. Please click on that.
box and arrow. Acha, okay. And then I'll have to share my slides. Screen share.
Yeah, the
Uh,
entire screen. Yes.
uh, Share and my document is here.
Yes. So
Just please check. Can you see these slides?
yes, we can see. Yeah.
Okay. Right. Thank you.
Yeah. Thank you. And who else? I think not other participants they yet join. So if they will join, then they may try. So we have still some more time.
Uh, okay. উল্টো ঘন্টা হুম পরিষ্কার দেখা যাচ্ছে শুরু হয়নি এখনো আমাকে টেস্ট করে নিল দেখা যাচ্ছে কিনা
So good afternoon, good morning, and good evening, all. So that depends where we are now. So, so we welcome you all for this inaugural already done yesterday. So it would be the first technical session for today. So actually there are two parallel sessions going on. It is 4A and there is another going on in 4B. So here we actually have less participants because most of the participants are in YouTube. I'm happy to announce that from yesterday we had more than 750 views. So intentionally we did not share much link for this direct meeting access, only for the participants and for the uh, uh, invited speakers are only being shared so that we should have less disturbance and all. So with that, I think today is a special day in India. So today is the National Mathematics Day that is due to Ramanujan, the great mathematician Ramanujan. So before starting the session, we have a small about Ramanujan. May I now request Professor M.R. Adhikari to give a brief talk about about Ramanujan's work and all. So it's a special day for India to celebrate the National Mathematics Day. So may I request Professor M.R. Adhikari to say a few words about Ramanujan.
Dear international audience, today 22nd December is the National Mathematics Day 2020 in India. I would like to say a few words about National Mathematics Day in India and mathematical contribution of Srinivas Ramanujan without entering into details. The Government of India declared December 22nd to be the National Mathematics Day. This was announced by the then Honorable Prime Minister Dr. Manmohan Singh on 22nd February 2012 at Madras University to mark the 125th anniversary of the birth of the Indian mathematical genius Ramanujan. Since 2012, every year, December 22nd, the birthday of Ramanujan is celebrated as a National Mathematical Day in India to honor Ramanujan's work in the field of mathematics. It is our great pleasure to say that on occasion of his 125th birth anniversary, our institute IMBIC dedicated to Ramanujan a research monograph entitled Contemporary Topics in Mathematics and Statistics with Applications, with 13 articles authored by renowned mathematician and statistician from USA, Germany, Canada, Switzerland, Japan, India, and some other countries, which was published in 1913. India is carrying on a long-standing glorious tradition of mathematics. For example, Brahmagupta, a scholar and mathematician, first time introduced the concept of zero called Shunno and its operation as a numeral in 628 AD. Without the invention of zero, the growth of sciences and human civilization would not be possible. Ramanujan is a mystery in the world of mathematics. He had almost no formal training in pure mathematics, but he made significant contribution to mathematical analysis, number theory, infinite series, and continued fractions. He solved many the then unsolved mathematical problems. During a short span of life, Ramanujan independently claimed nearly 3,900 results, mostly identities and equations. Many of them are completely novel. His original, highly unconventional results, now known as the Ramanujan prime, the Ramanujan theta function, partition formula, and the Mach theta functions, have opened up new avenues for research work. It is beyond the scope of the detailed study now, but nearly all his claims have been proved correct. Ramanujan's lost notebook is the manuscript in which Ramanujan recorded the mathematical discoveries of the last year of his life. It was rediscovered by George Andrews in 1976. Ramanujan became one of the youngest fellow of the Royal Society and only the second Indian member, the first Indian elected as Fellow of Trinity College, Cambridge. The British mathematician Ramanujan, Hardy, is known for his contribution in number theory and mathematical analysis, but he also was known for his adoption and mentoring of the self-taught Indian mathematical genius Ramanujan. Hardy told that the discovery of Ramanujan as a mathematician is his main contribution of his life. Ramanujan died 100 years ago on 26 April 1920. Ramanujan condolence meeting was held at Calcutta Mathematical Society. I had the opportunity to read the original proceedings of this condolence meeting. It was chaired by Sir Ashutosh Mukherjee, the then Vice Chancellor of Calcutta University, and a condolence message was read by Sir C.V. Raman, the great Indian scientist and the Vice President of Calcutta Mathematical Society. Raman won Nobel Prize in 1930 in physics. Thank you all of you for your kind attention.
Thank you, Professor Adhikari, for your donating description about Ramanujan, the great fellow, mathematics in India, genius person, genius mathematician without having any formal degrees much. Now may I request, it's my great pleasure to invite Dr. Lena Trell from Sweden to chair this session. So Lena, now it's yours.
Yes, and this ready. Oh, can you hear me? Can you hear me?
Yes, I can hear you, but some noise is coming. Let's see. Yeah, please.
Can you
Yes.
hear me?
Yes, we can hear you.
Yes. Then I will welcome you to the fourth technical session today, and we start with a talk by Dr. Shub MC, who will talk about the subject degree.
I think, sir, everyone able to hear Dr. Lena? Because I think not everyone's mic is muted. That's why it is some noise, maybe.
Did you hear me, or could you
Yes,
hear
now
me?
we can. We can yes.
When it's when did you hear what I said, or shall I repeat it?
I think formally, would you please repeat once again? Yes. Yeah, I think if you can repeat once again, then
Yes, and I welcome Dr. Shub N. Singh to talk about vertex degree in power graphs of abelian groups of prime power order. Please. But I think his microphone is muted. That's why we can't hear.
Dr. Shubhnaran Singh, your mic is muted. So could you please unmute it? And yeah, we cannot hear you actually. So Dr. Shubhnaran Singh, are you from Chrome? Are you using Chrome, Microsoft Chrome? I mean, not Microsoft, Google Chrome.
He doesn't seem to hear what we say either. We
Yes,
can't hear you.
Dr. Singh, are you using Google Chrome? Yesterday, we also had some similar problem. Uh,
Hello, can you hear me?
yeah, now it's audible. Yeah.
Can you hear me?
Yes, now we can hear you, but the sound is little less. So yeah, we can hear you. Please continue. Dr. Singh, we are not able to hear you. Please use Google Chrome. We cannot hear you.
Can you hear me?
Yes, now we can hear you. Some connection problem is there, I guess, your microphone and your machine. Sometimes it's giving you sound and not, sometimes not. Okay, maybe please try with your thing, and then we may go to the second speaker maybe, and then in between, I think we can have something that we can help, and your presentation could be continued. I think so. So I think it's better to go for the second presentation, and then maybe we can again come here. No problem. So I think some sound problem is there. Otherwise, everything looks fine. Okay.
Then I welcome Dr. Laxman Saha to talk about the study on metric basis for square of grids.
Hello, ma'am. I am audible. Hello, sir. Am I audible?
Yes, you are audible.
Yes, you are. Yeah.
Okay. Good evening to all. Thank you to organizer to giving me an opportunity to present my work in this reputed conference. So my screen is visible or not?
Visible.
Yes.
Okay. The title of my presentation is Study on Metric Basis for Square of Grids. Before going to that metric basis of square of grids and what are the definition of metric basis or code of a graph with respect to a set, just I am giving just a little bit definition of a graph. Graph is a collection of vertices and also the edges. Edges are the nothing but a association between two vertices. That association may depends on the characteristic of this situation. Here I have taken I have drawn a graph. The name of these vertices are A, B, C, D, and you see that we have made a connection between A and B. The distance between two vertices, we mean the length of the shortest path between these two vertices. So if we consider the vertices A and F, you see that we have a path to go from A to F. It is A, E, F, and another way we may go for A, H, E, F. So you see that the to reach from A to F, we need two length path. So the distance between A and F is 2. So the diameter of a graph means the maximum distance among all vertices of that graph. So if we take C and G, you see that these two vertices gets the maximum distances. For this graph, diameter is 4. So in that way, the definition of distance of two vertices and diameter is defined. So our topic metric dimension is related to some basic definition which are called as code. Now, when suppose a graph is given and we pick a set, suppose it is S1, S2, Sm, set of vertices, from which we can define code with respect to S as this quantity. What is this? What is this? Nothing but a distance between of a vertex B from each element of S. That means distance between S1 and B and distance between S2 and B. So if we refer this example, then it will be clear. So if we take this simple graph, this is called path graph. For this path graph, if we take U1 and U3 as S, then you see that the code of U2. What will be the code of U2? U2, you see that code of U2 will be here. U1 and U3 is there. So here one mistake is there. It is code of U2 will be 1 1. So from the U1, U2 has distance 1, and from U3 it has distance 1. So code of U2 will be 1 1. Code of U1 will be 0 2, and code of U3, you see that in that way. So code of a vertex means the distance of that vertex from each element of S. So you see that if we consider these two vertices for this graph, if we consider these two vertices V0 and V4 as the set, and for now we want to calculate the code of every vertex with respect to these two sets. So if we take the vertex V1, then the code of V1 will be 1 and 3. How it is 1 and 3? So for first vertex is V0 and second is V4. So for the distance of V1 from V0 it is 1, and distance from V4 it has distance 3. So like that we can define the code of each vertices. So now problem is that for a given graph there may be different types of we can pick different sets of different sizes, and we can calculate the code with respect to that set. So for example, if we take that circle type graph, then you see that if we take that vertex, then we can calculate the code of every vertices. And if we take these three vertices, blue shaded vertices, V1, V2, V3, then with respect to that we can also calculate the code of every vertex. Now, what should be the aim? So we have a different sizes set. So our aim should be to pick up a set which distinguish all the vertices. Now, what does mean distinguish of all the vertices? Means you see that if we pick only one vertices here, the code with respect to this set, it will be here, it will be 1, and also it is 1. So we cannot say that these vertices are distinct. This set distinguishes these two vertices. It cannot happen because the code with respect to that two vertices are same. But if we take here three vertices, this V1, V2, V3, then you see that the code of every vertices are distinct. That means they are distinct at least one places. So you see that so we can say that these resolve all the vertices. That means that coordinate, that code are distinct at least one position. Such type of sets are called resolving set. Now you see that we have for cycle type graphs we have a resolving set here of size 3. Now if we refer the figure 3, you see that if we choose two vertices V2 and V3, then with respect to that set, if we calculate the code of every vertex, here we also get the distinct code. So also we can say that this is also a resolving set. Now we can get so many resolving sets, but with different size. So our aim should be finding a resolving set with minimum cardinality. So it is a combinatorial optimization problem. How can we find a subset of vertices that will be a optimal resolving set? That means a resolving set with minimum size. Such type of set that is a resolving set with minimum size is called the metric dimension of that graph. So if we consider the path-like graph, then you see that just only if we choose V1, then all the code with respect to V1 are distinct. So path-like graph has metric dimension 1. So if we take the cycle type graph here, so we have a resolving set with cardinality 2. Now question is that is it minimal? So by a simple example, we can show that it is minimal. Why? Because if we pick this, if we assume that there is a resolving set with cardinality 1, then we always get a two adjacent vertices whose code will be same. So there cannot be a resolving set of size 1. So we, in that way, we can say that the cycle type graph always have a resolving set with the minimum cardinality, always have a resolving set with cardinality 2, and any set with one cardinality cannot form a resolving set. So in that way, we can say that the cycle type graph has a resolving metric dimension. Cycle type graph has metric dimension 2. So if we take a larger type of graph, that means if we take a power graph of some graph, suppose we consider square of cycle or power of cycle, then the adjacency property will be dense. So in such type of graphs, it is not easy to determine the metric dimension or optimal resolving set graphs. So that's why people are taking the particular type of graphs. In our presentation, we have considered the square of grid graphs. Why square of grid graph? Because by powering a graph, we can increase the connectivity of that graph. So that's why we have taken, and the square of that has lots of application in computer network. That's why we have chosen here the square of graphs and determine the what shall be the metric dimension for that graph. Okay. Now I shall define what is the square of graph. Some important existing results on metric dimension of graphs are such type of. One thing I want to mention here, that the such type of metric dimension problem of graphs has application in robot navigation or automobile system. There may be various application in that areas. So that's why, and those problems are only can be converted in graph theory. So that's why metric dimension is very important, but it has a difficulties, because there is no algorithm that can solve the such type of problem. That means the metric dimension problem is a NP-hard problem. But for particular graphs for any trees, it has been proved that can be solved by polynomial times. So here I have mentioned only few results which are existing. Tth power of cycles, t equals to 1, 2, 3, 4. It has been the metric dimension of that tth power of cycles is completely determined only for t equals to 1, 2, 3, 4. And some bounds are given in terms of any power of t. But till now, it is not determined the exact what will be the exact value of the metric dimension of cycle power of tth power of cycles. And for generalized wheel, the exact result is known. And for grid graph, the result is known, and it has been proved that the grid graph has metric dimension is 2. Now, what is the grid graph? So what is the grid graph? Grid graph means the Cartesian product of two paths. That path may have the same length or may have different length. So we denote that GMN as the, here we denoted here, GMN is the product of Cartesian product of PM and PN, where the PM denotes the length, a path with length L. And square of grid means square of grid is constructed from the grid graph, where the vertex set of the square of grid is same as the grid. But adjacency property has more connectivity. Now, what are the more connectivity? This connectivity is that are given by that two vertices in square of grid are adjacent if their distance is they are at distance 2 or less equals to 2. That's why. So if we delete these arc edges, then we will get the total grid graph, but we delete this, we add this type of edges, then we will get the square of grid. So we have completely determined the what shall be the metric dimension for the such type of graphs. So before that main result, just I want to say some definition which we have defined for a grid graph. we define some boundary of a ith row. Ith row means we define ith row. That means we consider this. If we consider tooth row, that means the vertices 2 0, 2 1, 2 2, and 2 3. This is called a 2th row. And 0th row means 0 1, 0 0 0 1, like that. And similarly we can define jth row. And we define the boundary of this grid graph. Boundary of this graph means that 0th row, and it may be 0th column, or it may be that boundary. That means that 0th row, that 0th column, and 4th row, and 3rd column. So square of grid has 4 boundary, and we name these boundaries as top boundary, below boundary, and left boundary, and it is called right boundary. So I have defined all this term, what is the boundary of this set and of square of grid. And in terms of because why we have defined such type of boundaries and top level or upper below level, because we have identified that the metric basis because we have to identify this that the basis element cannot be in the interior point, and we have proved this one, that that basis element must be on the boundary. And also we have shown that basis element must be the corner at corner of that point. So we shall prove that we proved that the metric dimension of square of grid is 3. So what shall be the position? What shall be the position of these 3 vertices? We have determined the completely what shall be the position of that vertices. Out of these 3 elements, we identified that 2 elements must be in the corner points. That means what it should be, if we take this grid graph, then we prove that 4 corner, 1 0 0, another is 4 0, another 4 3, and 0 3. So basis element must belongs to 2 basis element must be one of these 4 corner points. 2 of the 2 basis elements should be that quantity. And another condition is that remaining elements must be on the boundary. That means that 4 boundary, top boundary, left boundary, or right boundary, or it will be below boundary. So in that way, we can here we have described all these things, that for any metric basis, the basis element must be a subset of boundary, and we have proved that every metric basis must contains at least 2 points from same boundary. And another property also, every metric basis of GMN square must contain at least 2 corner points. By proving this result, we have determined that if we you see that we have mentioned it, you see that third one, every metric basis B of GMN square must contains at least 2 corner points. So here I identify that we have identified that what will be the what are the metric basis. Actually, we have determined all the metric basis of GMN square. So one result is that the metric dimension of GMN square is 3. So out of 3 elements, 2 should be corner point. So if we take the corner points as 0 0 and 0 n minus 1, then the one that remaining element must be one of these 4. So in that way, we have completely determined all the metric basis of square of grid graph, and the value of this metric dimension of GMN square is 3, and this is the okay, and these are the references, and thank you for your attention.
Yes, thank you very much. And are there any questions or comments to this lecture? If not, we go back to and see if Dr. Schab is connected. Can you hear me?
No, you are not still audible. Is your just could you please just sign out from the account and get into whether you have given the permission to access your audios and all. Please check. I think that may be a problem. While getting into this apps, you should give the permission to access your all devices. Unless you do that, it won't help you. So maybe yeah, maybe we can switch into the next speaker maybe and then
Yes, come back.
again.
But I shouldn't. Is it not better that he starts from the beginning? He goes out and then tries to come in from the beginning because I think something is wrong.
Yeah, might be, maybe.
Yes, I think he should try that.
Yeah, he actually I think got out and then maybe he will again come back. Maybe we can continue with the next speaker maybe.
Yes.
We can.
Then we welcome Dr. Smita Sonkar, who is going to speak about certain new factors on absolute weighted mean summability. Please.
Okay, good evening, ma'am.
Yes.
Yeah.
Yeah, you are perfectly audible. Can
Yes.
you please share your
Yes.
screen?
Yeah, sir, I want to share my screen, but sir, please help me because
Yes.
I
So
am
please
using Google
have a
Meet.
look at so please have a look at the box and an arrow. Can you
Yeah.
find a box and an arrow? Please click on
Yes,
that.
yes. Yeah, sir.
And then choose the entire screen or the desktop, the first one, first box. Please click on that box.
Because it's nice to see you.
Yeah, sir. Thank you so much, sir. Yeah.
You see the little camera and
Yeah. Visible?
Yeah, it's perfectly visible.
Okay,
Yeah.
thank you so much, sir. Good evening, everyone. Myself, Dr. Smita Sonkar. I'm assistant professor in Department of Mathematics, NIT Kurukshetra, and I want to present my research paper, Certain New Factors on Absolute Weighted Mean Summability. My presentation contents are objective, introduction, known results, main result, proof of theorem, corollaries, and conclusion and references. Now, first we start with the objective of my paper. An advanced theorem was established concerning the absolute weighted arithmetic mean summability under the poor conditions. So, first of all, from my presentation, I want to discuss about the summability. What is the summability? Actually, my research area is summability, and summability is a field in which we study the non-convergent series and sequence, and we attach a value to it, and after that, that non-convergent series to converge to that point. Suppose that, for example, 1 minus 1 plus 1 minus 1, this is a oscillatory series. Sometimes it converts to minus 1, sometimes it converts to 1, but by the help of summability we attach a value 1 by 2 it, and after that, that non-convergent series to converge 1 by 2, and with the help of Cesaro summability. So this is my research field, and in my research field, summability, this is a three types of summability. First one is a ordinary summability, second one is absolute, and third one is a strong summability. Here, this research paper is depending on the absolute summability, and mainly our field is a theoretical, but my field has application in the electrical department, electronics department. They are using our formula for the filters, like TIF, like IIR filter and bounded input, bounded output for a system. So now we start the our research paper. So an advanced theorem was established in this paper concerning the absolute weighted arithmetic mean summability under the poor conditions. Further, we have developed some new and well-known arbitrary results from the our main results. Summability techniques are used to reduce inaccuracy in any digital filter system. By using the appropriate condition, previous result can be easily obtained. So a bounded input and bounded output stability of drive is enhanced by absolute summability because it is necessary and sufficient condition for BIBO stability. Using these techniques, the output of the waves can be made more balanced and to analyze the behavior of input. So introduction, let summation a and be a given infinite series with the partial sum Sn, and which is denoted by un, and an infinite series an is said to be absolute summable if n tending to infinity un tends to a s, and with the bounded variation means if we are taking the un minus 1 and this is a finite, then we can say that a series converges to a finite number with the bounded variation, then that series is absolute summable. Now come to the definition second. The let nth Cesaro mean of NaN. If we are taking NaN sequence which is denoted by Tn, then this term represent the C1k summable. C1k summable, it represent the in the mod symbol, it represent the absolute C1 summable. Now third definition, let Pn be a sequence where P naught is a positive and small pn is non-negative. For n is a positive, we have defined this term from equation number 4. It means if here capital Pn is the sum of small p's and it tending to infinity as n tending to infinity. Suppose we defined here from this, we are defining p and alpha. The value of small p and alpha is this one, and capital P and alpha is the sum of small p and alpha. And whenever we are getting negative suffix, then it becomes sequence becomes 0 at that point where n is greater than or equals to 1. Then n bar represent the rees p and alpha mean of summation an is given by tn. Tn is this term here. If we are taking n tending to infinity, then tn tends to s and summation an is said to be rees p and alpha summable, means this is a absolute summable. Further, if sequence Tn, sorry, this is a only summable, but if sequence is bounded by also hold the bounded variation condition, then the summation An is said to be rees P and alpha k summable to S. If we define this factor Tn minus alpha Tn minus 1 k with this factor, then this is known as a summation an is known as a rees p and alpha delta k gamma summable, absolute summable, where delta is a non-negative and gamma belongs to a real number, and delta tn is defined by this equation number 9. Hey, let pn be a sequence with p not greater than 0 and pn is always greater than or equals to 0, means non-negative number for n is greater than 0, satisfying the condition number 4, means this condition number 4 satisfy. Then for alpha greater than minus 1 and beta is lies between 0 and 1, alpha plus beta is greater than 0, then define alpha epsilon 0 alpha plus beta is equals to 1, and alpha and alpha epsilon 0 alpha plus beta and epsilon and alpha plus beta is defined by this, and from this we are again defining the here p small p and alpha beta, equation number 11. So In equation number 12, if we are taking, if from equation 11 is defined for Pn, small pn, and equation 12 is defined capital Pn alpha, which is indicate the sum of small pn alpha beta, which is tending to infinity as and tending to infinity. Negative, whenever here also again, whenever we are getting negative suffix, then it will become 0 for n greater than or equals to 1. If Tn denotes the is P and alpha beta mean of series this, which is defined by this, and limit n tending to infinity and tends to s, then summation is said to be is P and alpha beta summable, formed by the sequence of the coefficient P and alpha beta. So here further, if sequence Tn is a bounded variation, if it also satisfy the bounded variation condition, then that summation An is also say that this is the absolute summable for Rees P and alpha beta to finite number S. In this definition 6, if this terms holds, then this indicates here we are taking the new factors delta and gamma. In the last term, you can see that there is a no alpha gamma, but when we want to more generalize the result, it means rate of convergence. If we want to increase the rate of convergence, then we are adding some factors. So here we are using the factor delta and gamma in this expression 15. Here delta Tn is defined by this equation number 16. So now come to the paper literature review. Board generalized the theorem dealing with the factors affecting absolute reasonability for infinites. Also, Bohr works on weighted arithmetic mean and gives many application of in this direction. Platt extended the theorem of absolute reasonability. Sonkar and Munjal determined various theorems on summability using conditions. In this paper, we have extended the result of Sonkar and Munjal as known result given below to determine generalized absolute reasonability factor for infinite series under poor conditions. So known result is Sonkar and Munjal have proved the result on absolute mean, which is defining for the delta gamma summable factor. They proved the result for the xn almost increasing sequence and Zion and lambda and satisfy the condition number 17, 18, 19, 20. With this help of these conditions, we have proved so series A and lambda and is Rees P and alpha delta gamma will factor. Now, here our motive is to derive two results using this known result defined already. Main result in the main result, first of all, I want to define the almost increasing sequence. A sequence is of bounded variation, that is lambda n, which is a bounded variate sequence. If delta lambda n is bounded variate, a positive sequence Gn is said to be an almost increasing if there exists a positive increasing Hn and there are two positive constants m and n, such that if this condition satisfy, then we can say that this is a almost increasing. The purpose of the main result is first to prove the theorem 2.1 under the weaker condition, and second to derive more generalized version of it. So these theorems are stated as: first theorem we have proved in this paper. Let suppose that x and xi and lambda and be defined as in the known result such that condition from condition 17 to 21, 23 holds from the known result, and we are and equation 22 and 24 in this 1 minute. Here we are using in our result 17, 18, 19, 20 and 21 as it is, and we are replaced 22 and 24 in the known results to it 25 and 26. Then we prove so here we are weakening the previous conditions and prove the result a and lambda n for this Rees p and alpha delta gamma k. So this is the same result, but we are proving in this theorem with the weaker conditions. And second theorem is depending on the generalization of the known result. So here again we are assuming x and xi and lambda and we defined as in the known result such that the condition 17 to 20 of result 2.1 are satisfied and equation 20, 21, 22 and 24 are replaced by the 27, 28, 29. So using these conditions we prove the result for the more generalized absolute summability factor. Here we are you prove the result for the delta gamma factor. The proof of our main theorem is we will prove first of all theorem 3.1. Firstly, we prove the theorem. Let Vn be the reason P and alpha mean of summation A and lambda n, which is defined by this Vn. And after Vn, we are getting delta Vn, and then we are using Abel's transformation in this term, and we break delta four parts v1 v2 v3 and v4. So for proving this result we know that here we are working on the absolute summability factor, so we need this expression less than infinite. So our main purpose is to find out the value less than infinite. So using one Minkowski inequality, we break v1 v2 v3 v4 as a v1 v2 mod of and mod of v3 and mod of v4, and one by one we are taking v1 v2 v3 v4 and calculate less than infinite, and then after collecting the result we will get the proof of theorem 3.1. So start, then equation 3.2 reduces to this, and then first of all, we are taking Z1 and here we are using Abel's transformation and condition 17 and 25. So we get the result order of 1 as m tending to infinity by using Abel's transformation and conditions 17, 20 and 25. We get the Z2 value. Z2 is equals to again order of 1. Similarly, by using Abel's transformation and using the conditions of 17, 21 and 26, so we get Z3 is equals to the form of order 1 from equation number 36, and at last 5 by using Abel's transformation and conditions 17, 21 and 26 we again calculate Z4 as equal to order of 1. So collecting 34 to 37 we are getting the 33. 33 is like 33 is this one. So our main purpose is less than infinite want to prove. So we are proving here is the order of 1, which is indicated it is a finite. So hence the first result is proved. Now come to the second result 3.2 in our research paper. Let un be the rees p and alpha beta. Here note that first result is only for the p and alpha. Now it is a very more generalized result because here we are generalizing the sequence as well as generalizing the method. So here we are using rees p and alpha beta. We are taking new factor beta and with the new formula. So un is equals to this one for n greater than or equals to 1. From here we are finding delta un. We know that delta un is un minus 1. From here we get this term by using Abel's transformation. So we are breaking this delta un into the 4 parts. So u1, u2, u3, u4. Again to prove the result 3.2, it is enough to prove it is this term is less than infinite. And note that here is a alpha with a beta. Using Minkowski inequality, we break this term into the u1, u2 plus u3 plus u4. Now again we are taking one by one and solve this. Now we are using Abel's transformation and condition 17, 27, 28. We get y1 is equals to order of 1 by using Abel's transformation and conditions 17, 27 and 28. We get the y2 is equals to order of 1, and by using Abel's transformation and condition 17, 27 and 29 we again get the order of 1. This is a calculation part, and by using Abel's transformation and condition 17, 27 and 29 at last we get 24. Y4 is equals to order of 1. So again collecting the equation 39 to 45 we are proving condition 41 which holds our result. We want to 40, so we here at last we get 40. So hence the second result is also proved. Now come to the corollary. This is a section for here we are proving some results from the our main results. If in the main theorem means our main theorem, if we take gamma is equals to 1 and delta is equals to 0, then it come out with a new result that is summation a and lambda is our series and it is a Rees pair alpha beta k summable, and this is the first corollary. In the second corollary, if we in the main theorem we are taking gamma is equals to 1, lambda is equals to 0, and here we are generalizing the result for the alpha beta. So here if we are putting beta is equals to 1, then another new result is obtained for the same series a and lambda and is a Rees p and alpha beta k summable. Now conclusion, here our main objective is to get negligible set of equations for absolute Rees summability. The idea of summability of infinite series has been applied in almost all application areas of science like rectification of signals in FIR filter, finite impulse response filter, and IIR filter means infinite impulse response filter to speed of the rate of convergence, orthogonal series and as well as in the approximation theory. Our concept of reasonability is also used to approximate the trigonometric Fourier periodic function and conjugate function and help the researchers of other areas of science who are working on the existing result of absolute reasonability. These are my references. Thank you.
And now, are there any questions or comments you would like to put forward? If not, we thank you very much. And
thank you so much, ma'am and sir. Thank you so much.
And how is Dr. Schub?
Excuse me, sir. Can you hear me?
Yes.
Yes, now we can hear you properly.
Thank you for your patience, sir.
Yes.
Yes. Can you continue?
Yep.
Yes.
Yeah,
you can start. We're welcome.
Yeah, thank you, madam.
And you're going to talk about vertex degree in power graphs of abelian groups of prime power orders. And now you can start.
Very good evening to all of you. Yeah, my topic of
your topic is
presentation is vertex degree in.
Yes, I can see
it. Group of prime power order.
Yeah.
So I find what is meaning of abelian group. So abelian group is just the result of applying the group application to any group element does not depend on the ordering which the other concept of a finite group is said to be P group if the order of the group is a power P where P is a prime. So that is meaning of graph. So this is the term defined by Kalrow and Queen in 2000. So directed power graph of a semigroup is a simple directed of S, and there is an AS V is generated. See, this is one example. I choose cyclics which have 6 elements. This one, and I construct Z6. So this is one example, and I choose the paragraph over S. After that, Chakravarti Ghosh and the concept of power. So power graph of a semi-group is nothing but an undirected simple graph whose of S and any two vertices are addressed if one of them is generated by other. I choose the cyclic or power graph. So see, this is the example of and power graph, example of power graph of order. So Chakravarti Ghosh and Singh in 2009 proved that the power graph group same paper, the power graph a finite group is complete if and only if prime power order. Bush in 2011 that any two finite abelian group with are isomorphic group. Same author that two finite group with isomorphic directed power graph have the same number of elements of each other. Cameron in 2010 proved that any two finite groups with isomorphic have the same number of elements of each other. Continued proved in 2014 among all groups of a given order and on cyclic group has maximum number. Chakravarti et al. In 2009 proved that the number of edges in power graph of finite group of order n set where mod of G other group C and this notation for cyclic subgroup and this identify function notation. This author proved that vertex degree of a vertex of the cyclic group is given by this. So my motivation to investigate in the power graph of finite abelian group where the degree of vertex is nothing or the vertex is nothing edges incident. So I notation talk for power. Another is in degree of G in a directed power graph. Third one is out degree of G in directed power graph and the size of set of bidirectional edges. So this is my first remark that in any of group finite group the vertex corresponding identity is the unique vertex or G minus 1 and out degree is nothing but 0. And for any non-identity element, we have out degree is nothing but out degree element, group element G is nothing but bidirectional degree is nothing but Euler 5 function of order of G. And we observe that if you want to find the any group element G, then it is sufficient to determine the by this formula determine the in the so for this we start the our so see this is will m1 m2 mn are integers satisfying this condition one and let the G will order of S e power m1 and in so that order of alpha is pt alpha, then in degree of x satisfied where d is but and k is the smallest non-negative integers, so that order of xk plus 1 power ik per non-empty element. Here we just corollary that if G is a cyclic group of prime power order, then the power graph a complete graph. Come to here concept. If your group is nothing but direct internal direct product of two normal subgroups, okay, where G is one element in G where x belongs to H and after degree of J satisfying this condition, degree of in degree this one, we prove this one. And by induction, we observe this result. We have a product of normal subgroup this one, where if you take normal subgroup HI and R of and if X G, then we can calculate the out degree of x, bidirectional degree of x, and in degree of x by this formula. And these are the my work. Okay, thank you to all of you.
Yes, thank you very much. And are there any questions or comments? If not, we thank you very much for an interesting talk. And then we go to Dr. Sapriya Pan, that is going to talk about crisis in cosmology and the role of dark interaction.
Thank you very much. So can I share my screen?
Yeah, please.
Okay. So is it visible and am I completely audible?
Yes.
Yes, both.
But we can't see you.
Sorry?
We can't see you.
Okay.
I think in Microsoft team both will be difficult to adjust.
So should I turn on the video, sir?
If you wish, it's up to you.
Okay, I think for a better network connection, let me turn off the video.
Yes.
Okay.
Yeah, I think so.
You see the little camera and you press it and can you see the little camera and then you take
he
the...
can.
Yeah.
It will consume much data. That's why he's afraid, so that his presentation may be little delayed or something. Interference may come, or bandwidth problem might have. So please continue without camera.
Yes.
Then.
Okay. So I must thank the organizers for allowing me to present in this international conference. And I'm going to talk about a very interesting topic, which has been one of the foci of recent cosmology. It is the crisis in cosmology and the role of the dark interaction. So we're already very familiar with some biggest news of cosmology. That means the accelerating expansion and the detection of the gravitational waves and some others. So in this talk, I'm going to discuss about a very recent detection by the supernova type 1a observations, and that has created a crisis in the cosmological sector. And that is why I have taken this title to be the crisis in cosmology. So this is the outline of my talk, where I will start from the beginning of the lambda cold dark matter cosmology, which is the effect of the accelerating expansion of the universe. And then I shall discuss about the crisis in cosmology that has been created from the lambda cold dark matter cosmology. And after that, we shall discuss how we can avoid the crisis in cosmology and if we can have some alternative solutions to reduce the crisis or solve the crisis. And finally, I will summarize with some future experiments and the main results of this talk. So let us begin with the lambda CDM paradigm. So basically, lambda CDM is some cosmological model where a cosmological constant together with some cold dark matter is associated, and this is the best cosmological model so far which can describe the present day observational evidences of the universe. But the question naturally arises, and this should be the most basic question whenever everyone would like to talk about the cosmological solutions, is why do we need the lambda cold dark matter cosmology? So if we want to understand the need of the lambda cold dark matter cosmology, we have to go back at the end of 1990, where the observations from supernova type 1a detected that our universe is presently going through a phase of accelerated expansion instead of the decelerating expansion that was theoretically predicted. So naturally, whenever the observations from supernova type 1a appeared with a fantastic and finest discovery of the accelerating expansion, the cosmologists became very afraid because a specific astronomical data are indicating the accelerating expansion. So naturally, a lot of astronomical missions started to investigate the feasibility or the viability of the measurements of supernova type 1a. And as a result, different astronomical missions started investigating the same result from different perspectives and from different astronomical data. And finally, it was proved that the observations from supernova type I were actually correct. That means the universe is actually accelerating. And that is why the 2011 Nobel Prize in Physics was given to the scientists Adam Rees, Perlmutter, and Schmidt for discovering this accelerating expansion. So anyway, it has been already proved that the universe is accelerating from the observational data. So naturally, we have to understand whether we can have some theoretical formulation that can match the observational predictions. And this is the beginning of the cosmological constant, because the cosmological constant was already proposed by Einstein long back ago, but it was again revived and included into the Einstein's field equations in order to understand why this accelerating expansion is happening at present. And so the cosmology is actually full of mathematics, but here we shall show why the crisis is actually coming and how the cosmological constant is creating this kind of crisis. So this is the Einstein's field equations, and if we want to look at the explicit formulations of the Einstein field equations, we have to consider, or we have to take some very simple mathematics. The simple mathematical equations are, we have to take the metric, that means that characterize the geometry of the universe and the matter distribution, and whenever we take all the information and put everything into Einstein's field equations, we have a couple of differential equations. So one is the Hubble equation and one is acceleration equations. So basically, we are dealing with the differential equations in order to understand the cosmic dynamics of the universe driven by the lambda CDM cosmology. So far we have the differential equations, and people wanted to understand the accelerating expansion, and lambda was very fine to explain the accelerating expansion, and with a lot of observational evidences. It was proved that lambda CDM is working very fine. But as long as people try to understand the deeper property of the lambda CDM cosmology, and basically whenever the understanding of the cosmological constant became very powerful, people discovered that the cosmological constant is suffering with two very serious issues. One is the cosmological constant problem, and the second is the cosmic coincidence problem. The cosmological constant problem is a very biggest problem in cosmology, because the cosmological constant is a time independent quantity, and whenever we are measuring this cosmological constant from observations and from theory, we are getting to different values, and these two different values are very mismatching, and up to the order of 10 to the power 121. So whenever a particular quantity is mismatching from two different perspectives, that means we have some problems within the theory itself. And naturally, there is one more question, which is the cosmic coincidence problem, in the name of cosmic coincidence problem. And it raises a different question in the form of why the matter density and the energy density of the cosmological constant are of the same order. So cosmological, the lambda CDM cosmology was suffering with the cosmological constant problem and the cosmic coincidence problem. But since 2016, and probably at the end of 2015, some observational evidences further indicated that the lambda cosmology is not only suffering with the cosmological constant problem and the cosmic coincidence problem, but this is also suffering with a very serious problem in whenever we are measuring some key cosmological parameters. And this is the beginning of the crisis, because whenever we are trying to measure some very key cosmological parameters, this kind of cosmological parameters are returning to very different values, and the differences between their measurements are many sigmas apart. So we begin the discussion with the Hubble constant, because this is one of the key cosmological parameters, and this is actually tensed. We are using the word tensed because the Hubble parameter, whenever we are measuring from two different astronomical missions, we are getting to very different values, and the differences are increasing from 2016. That means in 2016 we estimated two different values, and now in 2019 the differences are basically increasing. So the tension, which is quantified by the differences of the particular parameter values, is actually increasing. So this is the Hubble constant tension at present. So how to measure the Hubble constant? So there are basically two different ways. One is the measurement from the early universe in terms of the cosmic microwave background radiation, and one from the measurements of the late universe. That means we can use the local observables. So whatever the process be, we are basically measuring a particular cosmological parameter using the early universe information and the late universe information. And if we get exactly same values or similar values, then we are fine. But whenever we are measuring the particular cosmological parameter and we are getting to different values, that means either we have some systematics in the measurements or we need some different alternative cosmological models. So from the CMB, that means from the cosmic microwave background radiation, whenever we use the information from the cosmic microwave background radiation, we basically need a specific cosmological model. And since lambda CDM is the finest cosmological model, so it can be used to estimate the Hubble constant. So Planck, using the cosmic microwave background radiation within the minimal lambda cosmological module, estimated the Hubble constant, and they are basically like 67 point something. So they estimated the values of the Hubble constant, and the estimated values are around 67 point something. On the other hand, same Hubble constant, but they found that the Hubble constant estimations are like this. And interestingly, this collaboration did not use any model in order to estimate the Hubble constant. So naturally, we are using two different mechanisms. One at the background of some cosmological model from Planck, and one the model independent approach, and we are basically getting to different values. That means either we have some systematics in the measurements, we have some errors, or it may happen that the background cosmological model lambda CDM is no longer valid. The problem with the measurements, whenever we are talking about the systematics, and it has been already argued by many observational teams, that the systematics cannot describe such differences. The only possibility is the problem with the lambda cosmological models. And that is the basic crisis in cosmology, because we are getting to different values, and such values are basically very they are basically differing from one another at many standard deviations. So why should we believe the S80US collaboration? So we have to also check the estimation of the Hubble constant from other observational evidences. So fine, we can also consider the estimations of the Hubble constant from other observational evidences. And here I have basically shown the measurements of the Hubble constant from the late universe and the early universe, and where it has been found that whenever we are considering the late universe, the Hubble constant measurements are 73, 73, 72, etc. And whenever we use the early universe information, this is actually 67. So there are a lot of observational evidences that confirmed that the estimations of the Hubble constant from late and early universe are very different. And the estimation of the Hubble constant was also carried by another collaboration. This is H0-Likau collaboration. And they also found that the Hubble constant should be around 73 instead of 67 that Planck detected. So it is very much true at the present level that the tension in the Hubble constant is increasing, and that tension can be quantified through this particular diagram, where it has been found that the tension between Planck and local measurements are increasing day by day. So that means we need some alternative cosmological theories that could explain this discrepancy in the measurement of the Hubble constant. So anyway, so naturally the questions, whether we have some systematics or the alternative cosmological models, whatever it be, we need some new investigations in the light of recent observational data. So there are basically two different ways. Either we can introduce some different cosmological models in the context of general relativity, or we can directly modify general relativity. That means we can directly modify Einstein's theory in order to understand why these kind of tensions are appearing in the context of cosmology. So there are basically two ways. So one is the general relativity and the modified gravity theories. So we are basically trying to understand the cosmological tensions in the context of general relativity, because that is much more simple compared to the modified gravity theories. In the context of modified gravity theories, there are some unnatural problems that automatically appear. So whenever people wanted to investigate the tension in the context of general relativity or in the context of modified gravity models, a number of cosmological models were proposed. There are several alternatives that can be considered to be the viable approach to understand the H0 problem. So I have already listed a few of them, and here I am interested to describe the first possible resolution of the Hubble constant problem that appears in the context of the interacting dark energy theory, because interacting dark energy theory is a very viable approach where it is given that the dark matter and the dark energy to heavy fluids of the universe can interact. Actually, this is a very general framework in cosmology, since the nature of dark matter and dark energy are unknown. So it is a very natural thinking that an energy flow between these dark sectors may happen. If I consider a general theory by allowing an interaction or energy flow between two different sectors and test the particular cosmological scenario in the light of latest observational data, then we can infer whether the observational data are favoring the interaction model or not. So basically, we are considering a specific theory of cosmology and we are testing them using the latest observational data from various. So let's describe the model of interaction. This is a very mathematical theory. The theory of interaction is a very mathematical theory where it is given that an energy flow between dark matter and dark energy is, that means the dark matter and dark energy are jointly conserved instead of their independent conservation. The mathematical equations of the interacting dark energy are very simple because we are just trying to understand the joint conservation equation of dark matter and dark energy. So by these two equations, we can understand how the dark matter sector and the dark energy sector are evolving with the cosmic time. But the most important point in this context is what about this particular Q? Because as we have shown in this particular equation, this is actually a very general function. It's a very general function that determines the transfer of energy between these dark sectors. So usually if I give any specific functional form for Q, we can either numerically or analytically determine the evolution equations of the dark matter and dark energy. And whenever we have the evolution equations for dark matter and dark energy, we can have the entire evolution of the universe. That means we can determine the expansion history of the universe. So naturally, for any specified Q, we can determine in principle the cosmic dynamics. But the question arises, what should be the possible choice for Q? Usually it is assumed that the Q is phenomenological because I can put any continuous function for Q and I can determine the cosmic dynamics, but that should not be the case because we cannot take any particular Q and test the cosmic dynamics and consequently model with the use of observational data. We have to be very much specific and we have to follow everything from some general principle or some action principle. So what exactly we did, we derived this particular form of the interaction function from some field theoretic arguments where this phi1 is representing the dark matter sector and the phi2 is representing the dark energy sector. And after a lot of calculations that have been shown in this particular work, we derived that this kind of interaction functions follows from this action principle. So we can just take the interaction function from some field theoretic argument and finally we can determine the cosmic dynamics. So what is happening here? We are studying everything from some field theoretic argument and we are trying to understand the cosmic dynamics using the observational data. So our theory is motivated and naturally the model is getting motivated from the theoretical perspective and finally we are using the observational data. So basically we are considering a very well motivated cosmological theory and then finally we are trying to understand whether the well motivated cosmological theory can resolve the Hubble constant tension or not. So this is a very important question at this point. So we already have the choice for the interaction function and whenever we have this interaction function we can test the background cosmological model and exactly we used a lot of astronomical data, this cosmic microwave background radiation from Planck, baryonic acoustic oscillations, local measurement of the Hubble constant, supernova type 1a, Hubble parameter measurements and everything. So we considered a lot of observational data and finally we tested our model with the help of these observational data and we also used a very fast and advanced cosmological package CosmoMC and it needs a very high computational machines in order to extract the cosmological parameters. So we started our investigation with a very simplest cosmological scenario by assuming this W to be -1. This is W to be -1 and with this particular model. So whenever we are assuming this W to be -1, that means we are actually interacting some vacuum with the cold dark matter. So that's a very simple cosmological scenario and we the Cosmo MC, and we estimated the Hubble constant. So naturally, we can see whenever we are estimating these cosmological parameters, the Hubble constant is taking around 71. And whenever we are adding this particular CMB and this R19, that means H0 value, we are getting the 73 point something. So that means the Hubble constant is taking the values which are very close to the estimation of the SUS collaboration. So that's a very simple cosmological scenario where we allowed vacuum to interact with the cold dark matter, and we extracted the cosmological parameters, and finally we just displayed a very specific, there is a control plot, and which shows that as long as this J, the coupling parameter, is increasing, the Hubble constant is actually increasing. That means there is a correlation, strong correlation between the Hubble constant and the coupling parameter. And this is clearly visible from this particular plot. That means the Hubble constant problem is alleviated. We can say that it is perfectly solved, but it is alleviated. It was earlier around 67 point something, and now it is more than 70. So basically the Hubble constant problem is alleviated for this particular cosmic scenario. So naturally, the next question that automatically appears, why should we consider this W to be -1? Why can't this W2 be a free parameter other than -1, and we can see whether the same scenario is happening or not? Because it may be considered that this is happening because of the consideration of W equals to -1. So naturally we can consider this W constant and play the entire game. So it has been also found that if I consider the same model with this constant W which is not equals to -1, then again the Hubble constant problem is alleviated. The Hubble constant problem is again alleviated because the Hubble constant, the estimated values of the Hubble constants are very close to the estimated values of the SUS collaboration. And this is actually happening for the phantom case instead of the quintessence case, because that means this table actually. And if we look at the contour plots, we can see that for the phantom case we are basically getting very high values of the Hubble constant. Everything was done in Cosmo MC, and all the results were obtained using various observational data. That means Planck plus BO, Planck plus R19, etc., etc. We then naturally wanted to see that whenever the Hubble constant problem is alleviated for W equals to -1 and W equals to constant other than -1, so can we consider that means can we have the same alleviation if we consider a dynamical W? And we investigated the same problem with the dynamical W, and the form of the dynamical W is something like that, where Fa is any continuous function. Fa is any continuous function. That means it is independent of the choice of the particular functional. We basically considered 5 different scenarios. That means 5 different functional forms for Fa. But finally, we found that the result remains same, independent of the choice of this particular function. So that means if I consider an interacting scenario where the equation of state of dark energy is either -1 or constant or dynamical, the result concerning the estimated value of the Hubble constant shows that the tension is alleviated. But if I consider other cosmological theories where it may happen that whenever we consider, that means what exactly we're doing, we are basically extending the lambda CDM cosmology by including an interaction in the dark sector. And this is a very general scenario. And that general scenario is again generalized by considering different variations of dark energy. That means our theory is much more flexible. Because since whenever a theory is much more flexible, that means whatever we do with this particular theory, the results are not basically changing. The results remain same independent of any variations within the particular cosmological theory. But if I consider a different cosmological theory that we also have tested, we have found that whenever we change something within the theory, and everything collapses. That means we have to consider a stable cosmological theory, which is the interacting theory, where if I consider different variations of the dark energy model, our results do not change. So that is the essence of the interacting dark energy theories. So we found that independent of the nature of the dark energy, whenever we allow an interaction between dark matter and dark energy, by some specific functional form characterizing the interaction between them, and this is totally motivated from the perspective of the field theory, then we can alleviate the Hubble constant problem, which is a recent crisis in cosmology. So that means this can be considered, the interacting model can be considered as a possible way out to ease the Hubble constant problem. So this is what exactly I wanted to present in this conference. So let us just summarize that the tension in Hubble constant has definitely created a crisis in cosmology, because the lambda CDM has been challenged by recent observations. The lambda CDM, which is one of the best cosmological theories in agreement with a lot of observational data, has been challenged by the recent observations from supernova type 1. So naturally, this is a crisis in cosmology, and the interacting dark energy model can alleviate the Hubble constant problem, but still we cannot solve everything in cosmology. That means we need further investigations, and up to present time we have a lot of observational data from different astronomical sources, and based on them we found that okay, based on the present observational data, we can alleviate the Hubble constant problem, but we can't solve everything perfectly. So we have to wait for more data from other astronomical missions, and the future astronomical missions are investigating, and they have planned to release a lot of observational data in near future. For example, already we have the future CMB observations from Atacama Telescope and South Pole Telescope. So basically they are trying to understand, they are trying to gather a lot of observational data. And the future local data astronomical surface, something like dark energy spectroscopic instrument, Euclid, Rubin. So the motivation of all such future experiments is to understand whether the whether the problems in cosmology and the nature of dark energy can be revealed. And if we can have much more precise measurements, we can have a very precise conclusion on the Hubble constant problem. So basically, we have to wait for more data in order to understand the Hubble constant problem and its status in near future. So thank you.
Thank you very much. Any comments or questions? If so, we thank you very much and go to the next speaker. That is Dr. Moitri Sen.
Hello, am I audible?
Yes. And you are going to talk about influence of Ali effect on the predator system with hunting systems with hunting cooperation. So please.
Okay, so I can share the screen now, right?
Yes, please.
So it is visible now?
Not yet.
No.
Is it?
You see the little camera beside the microphone, and if you press it to take the line or
No,
cross away.
Okay. So is it visible now?
No. Can you see the little white camera or beside the microphone?
My screen is not visible?
No, your screen
No.
is not visible.
Actually, I've shared the screen. It should be visible. Okay, someone is, I think, presentation mode is on. Supriya,
No, I think the presentation mode is on.
I don't know.
No,
I
no,
can see on the
I have
list
stopped sharing.
that your camera is crossed over.
Yeah, maybe. I'm not sure.
You see the little list.
Yeah, I know.
Camera presentation will be different from camera. So
Okay.
Yeah,
box
presentation is different. That I know how to, because I am acquainted with this. So let me try again. Is it visible now?
No, not yet.
No.
I don't know. It's not visible, right?
So you have to click on the share option, I think.
Yeah, that I know. Actually, I already shared.
Okay. So
No, it's not exactly.
Could you please log in again? Then maybe something may happen.
Yeah, I can. Okay, I'll just try.
So you are doing it from Chrome or your installed software?
My installed software.
Okay.
So let me just try again.
Yes. Yes, now it's fine.
Yes.
Is this right? Okay.
Yeah.
Okay, thanks. So thank you all of all the organizers and also the participant, and mainly sir, Dr. Abhishek Adhikari, for inviting me and allowing me to present my work. So I'll be mainly speaking on the influence of alley effect on the proprietor dynamics with the presence of hunting cooperation. So this is the mainly my outline of the talk. So basically, I'll just give a brief introduction because it is a very diverse audience. So and also I must congratulate the organizers because for holding such a diverse conference. So I'll just give a brief introduction about proprietor interactions and all, and then what is alley effect and its applications and its influence in ecology, and the model that we are proposing and what are the results, and then it will subsequently I'll present the conclusions and references. So in ecology there are mainly two types of interactions. One is intraspecific, one is interspecific. So the intraspecific interactions mean that the interactions are between the individuals of the same species, and interspecific, as we can understand from the term, that it is between two different or two or more different species. And widely there are three types of interactions that are observed. That is competition, predation, and herbivory. And one is symbiosis. So competition means if there is any if there is any interactions between the same species or different species who are hunting or driving for the same resources or something. And predation is means there is one or more prey, and there is one or more predator who kills the prey and for their food and all this. And herbivory means that they will invade or feed as a photosynthetic organism. And symbiosis are mainly in between two or more species who are living in direct contact with each other. So I'll be mainly speaking on the predator-prey interactions here. So the second one. So the basic predator-prey model, this is a very famous diagram that I wanted to show, that this lens array data which actually support the predator-prey models, and that was initiated by Lotka and Volterra at the same time in 1930. On 1929 actually, both of them have done the same work around the same time also. So these are some examples of prey, and these are some examples of their predators. So in classically, what is assumed that at low density, the constraint of interspecific competitions, it releases. That means whenever we are few, there are more resources, so there will be chances that we survive also in a better way. So because the resources are more, so there will be greater availability, and the population, even if they have a low density, it will come back to their intermediate densities or higher densities. So in view of that, generally the models, or generally the prey predator models, are defined or modeled in this type. So basically the Gauss type model is given by these two differential equations, where if n is the prey, p is the predator, and then this afn is a function of wholly is a function of n, which represent the per capita growth rate of prey. Gn is the function wholly of n, which represent the functional response, and so on. But there can be not only the functional response not only depends on the population n only, I mean the prey only. It may sometimes depend on the both the populations. That means that will come later. So there can be different types of functional responses. So that's why it can be also a function of both n and prey and predator. And these are the notations or whatever that is represented by this. So E is the conversion efficiency. That means whatever the predator consumes, is how they converts to their fitness or their densities. And because of the classical notion, mainly the functional form of F, or the per capita growth rate, is given as a logistic growth. That means it will grow as a logistic function. And but in 1931, ecologist W.C. Alley-Fast reported one thing, that he observed that in a pot or in a tank full of goldfishes, that when there is goldfish already present in the water, the growth rate or the rate at which it grows is higher than when there is no goldfish. So and after that there are many works that has been done. So that at that time he and after that also he done different types of experiments and all to understand that fact that why it is differing from the general notion or the classical notions. And he came up with the idea that in ecology there is an effect other than the classical notion. There are actually populations which follow this type of growths. That means and then came and after that came the name of alley effect. So alley effects means that there is, so I will come to the analytical or the formal definition, but before that I'll just to mention some of the references that actually uh, gave proper definitions from the observation of W.C. Ali, because he never gave any definitions or anything of the Ali effect that we know now. He just observed few things and reported those results. So after that, so in these papers, the authors have actually documented that and gave a proper definition or gave, I mean, throw light on those the effects and its, I mean, uh, what are the its effects on the general ecological system or epidemiological systems. So mainly when we can expect or we can observe the alley effects. So it can happen. So these are the alley effects mechanism. So in population, if there is a broadcast band spawning, then there are several species who actually suffers from this mechanism and can have alley effects in their growth. So these are some of the mechanisms that can produce or that can give rise to alley effect in the population. So some species which shows alley effects are this bluefin tuna, kakapo bird, and these are then so there are many types of species that actually shows different types of alley effects, because there are different types of alley effects in the in nature. So these are some of them. So if now coming back to the formal definitions, so there are two types of alley effects. One is component alley effects, one is demographic alley effects. So component alley effects is actually if it shows in some component of the population. So if the alley effect is can be seen in a component of the fitness or population, then it is called component alley effect. And demographic alley effect means if it is observed over on the whole population. So the causes of the alley effect that I already discussed, the some mechanism is mate finding, social dysfunctioning at the small population sizes, inbreeding, depressions, food exploitations, and many more. So now what is alley effect? So how can you define that? So there are two types of alley effect mainly, and it means that the per capita growth rate at the initial level is increasing in its low density. So there are two types. We can divide that alley effect in two types. One is strong alley effect, one is weak alley effect. Strong alley effect means that per capita growth rate will be low at low density will be negative, and the weak alley effect means at zero density the per capita growth rate of that population will be positive. And whenever we include or whenever we model a system, if we want to incorporate the LA effect, so there are many ways. So mainly we follow two ways. One is multiplicative, one is additive. So there are two ways of incorporating LA effects in a multiplicative way, in an additive way. So if I show it in a diagram, then so the strong LA effect, you can see that. So it's basically at low density, it is negative. For weak alley effect, it is at zero density and onward, it will be positive. It never goes down. That means this curve, so it will be always positive. And for the logistic growth rate, it is this curve, logistic curve. But actually, this is not very sensible. This curve, logistic, I mean, not every ecological system or not every population can be, I mean. or subjected to this logistic growth rate. So it is obvious from this graph also. So mathematically, if we formulate, then for strong LE effect, actually it is the function phi such that it follows these conditions, these simple conditions, and for weak LE effects, there will be some parameter or some number k such that it will happen, and then onward it will be positive. So I will discuss some forms of phi. So there may be different types, as we already mentioned, that there may be additive, there may be multiplicative. So there are many ways to incorporate LE effect into the system, given into account how the population behaves. So there may be this type, this phi n can be of this type, phi n can be of this type, and phi n again can be of this type. So if we plot, then we can see that the growth rates, if we compare, it will vary in a different way. So definitely it will choose the alley effect depending on the system that we are having on our hand. So it will differ from system to systems. How do we formulate or how do we model that system, including the alley effect? Next, we come to the functional response that we already talked about, that the GN function. So first, initially in a Gauss type preparator model, the functional response is always a function of prey. So it was believed that the functional response, that means the predator can predate the way that predation rate and the how it can predate only depend on the prey. It cannot depend on predator. But there are many examples, and there are many work that has been done, and there are many ecologists that have already reported that it is not the case. There can be different types of function response, including that it is dependent on the predator also, not only prey. And ratio dependent is one of them, and one very important and very famous is Beddington dangles. So it depends on both the prey and predator. But the thing is, if I can go back to the slide, so you can see yeah, here you can see that E is a parameter, right? E is the conversion efficiency, and we don't know E what will be E, and this GN is also we don't know what whatever the GN is. So E and all those things, it becomes a parameter. So it is not depending on the population. So it is independent of the population. It is believed, generally it is believed, and classically also it is believed. But very recently, not very long ago, but very recently, there are few works that can be seen that is fastly observed by Luca Beric, and he discussed in this paper that GN, that means the functional response, can be of this form. That means lambda, whatever that was E, or here whatever the parameter, that can also depend on the predator. It may depend on the predator, and also there are many examples. Now, what are the examples? So how do we define, or how do we actually what are the implications, or what are the what should I say, this lambda p, what does it demonstrate? So this is actually means that there is a if there is any cooperation when the predator is hunting a prey, if there is a cooperation, that means this functional response is not only solely dependent on prey itself. So if there is a cooperation, then there may be cases that whenever a predator forage with cooperation, so they can forage better, they can survive better, and whenever they are going lonely, they can be even killed, right? So we can see it in cow and lion. So if the lion goes, if a bunch of lion go for predation, and there are few cows, then automatically they will kill them and they can get food and easily. But if the case is reversed, that if there is one lion or two lions and there are many, I mean a bunch of cattle, then the case may be reversed. So the predator may be killed. So that means the cooperation is a very important thing in predator-prey systems. So generally it is believed that the predation actually enhances the chance of sustaining a prey or sustaining the prey-predator system in a better way. So, and the Berek was the first person ecologist who observed that and also suggested that the functional response can be formulated this way. Then recently, very recently actually, this Hilker and Alves, they borrowed that idea of Berek actually, and they gave an simple example that okay, let's take the lambda p to be a very simple linear function of lambda p, and see what are the implications of that on the systems, on a prey-predator systems. And they saw that it actually enhances the hunting cooperation, or what that simple incorporation of hunting cooperation actually enhances the scenario of coexistence. And also it was very interesting that they worked with in this paper they worked with a type 1 functional response. We call that this type 1 functional response. So in generally in classical models there is no bifurcations occurred, or whenever whenever the equilibrium point is there, it is always stable. But incorporation of this hunting cooperation gives rise to the fact that actually there are possibility of periodic solutions of the system, and there can be different types of bifurcations also. So they reported these results. So that was very motivating. And also later there was some works was done, and in those works also it was reported that in presence of alley effect also the stable coexistence may persist, or maybe actually it can actually enhance that stable coexistence for specialist predator. So in our work actually we took one prey-predator model, simple prey-predator model, where the prey is subjected to the multiplicative alley effect, and we have taken the same type 1 functional response with the hunting cooperation in with the linear form of lambda p, and we have taken a generalized predator. Now what is a generalized predator? Generalized predator are those who can survive without the given predator also. So there are many examples of predator who can survive on their own without the predator also in the system. So we thought, well, let's see what will be the what will the effect on those animals or those predators with the presence of alley effect in the prey. So then after to minimize the parameters for the simplicity or sake of simplification of the calculation, so we non-dimensionalize the system and it becomes like this. So in that we observe that there may be 6 equilibrium points. One is trivial 0 0 equilibrium points, beta 0 and 1 0 0 1, and so it's I think because in the case of weak alley effect also it can happen, and so and there can be one or more interior equilibrium points. Now in predator-prey dynamics in ecological systems, these interior equilibrium points are of great importance. Why? Because we always look for the coexistence of these equilibrium points. So that means we want the system to coexist always it's nowadays it's a very alarming situation, because coexistence is becoming a very tough thing to happen in the world. But in preparator in ecology. Mainly we want to see what are the parameters or what are the effect or how any system can coexist. So mainly we look for the stability of this E star or E1, E2, whatever it is, equilibrium points. So we see what are the effect or what are the parameters, what are the system parameters or outside parameters which can affect the system's interior equilibrium points to coexist, or if not, what are the parameters that making this system to going to making this system go to extinction. So now if we draw the null clines means basically here I just want to mention because maybe these things may not be familiar to everyone. So null clines means so equilibrium point means what? Equilibrium points whenever F1 and F2, this capital F1 and F subscript 1 and F2 F subscript 2 is 0 at a time. So the roots giving these two roots of these two equations. And null clines means if we draw the equations of these two equations, leaving out the zero term. That means leaving out n here, n from here first equation and p from the second equation. So if we draw them, so interior equilibrium points are the actually the intersection of the null clines. So there may be, so we can see from the positions of the null clines that in each case there can be one or two or no null clines, right? So I here I want to just mention one thing. See, in the first case, that if we change the parameter, then the red null cline, that is the predator null cline, can be can go, can touch the prey null cline tangentially. So in this case is called as this has a special name. It is called the saddle node bifurcation point. So after this, if we change the parameter more, then there will be no interior equilibrium point. So this, in this case, there will one bifurcation occur. So similarly, so that means there can be either 1, 2 or no interior equilibrium points. And these are the stability results. As we are saying that we want to check the stability of the interior equilibrium point with greater interest. So let's just first our knowledge that these are the results for the other equilibrium points. Now, what is the stability? Stability is actually if we find the the eigenvalues of the Jacobian at these points, at these interior equilibrium points, then if the Jacobian is having, in this case there will be two eigenvalues. So if all the eigenvalues are negative or the real part of the eigenvalues are negative, then it will be stable. If one of the if the real part of one of the equilibrium point is positive and another is negative, then it will be a saddle point. And if both of them are positive, then it will be unstable. Okay, so these are the conditions that we are having. Now in the case of weak alley effect also, these are the conditions that we will obtain. Now for the interior equilibrium point, analytically it becomes very difficult. So using the help of the vector fields, we can prove that this equilibrium point, that means E2 star, can be stable, can be unstable, and can be and can change its stability from stable to unstable. But the U1 star, that means another interior equilibrium point, will never be stable. It will always be a saddle point. So now in this problem, there may be different types of bifurcation. So what is a bifurcation? So bifurcation basically by the name of it itself, it suggests that means if there is a scenario, if some scenario is getting bifurcated from a certain scenario, right? So that is the bifurcation. So in nonlinear dynamics, there are different types of bifurcation. There are local bifurcations, there are global bifurcations. So local bifurcation means what? Which is attributed to the equilibrium point locally. Okay, so say the change of stability or change of occurrences of number of equilibrium points and so on. And the global bifurcation means what? It is not related only to the equilibrium points, but more globally. Suppose there is a periodic solution. If that periodic solution is getting deformed, or maybe it is suppressed, or disappears, or appears through something, so that is called a global bifurcation. So now the first local bifurcation that is observed in this case is transcritical bifurcation. Transcritical means what? Where one equilibrium point is always present there. It is not disappearing or appearing. It is always present there, but after a certain threshold or before a certain threshold, the stability of that bifurcation is changed. Okay, suppose a bifurcation is stable up to a certain point. After a certain point, it becomes unstable. So that is called a transcritical bifurcation. So saddle node bifurcation that I already mentioned, if there is a appearance or a disappearance of two equilibrium points. So suppose two equilibrium points coincides at a point. So that point is called a point of bifurcation, which is called the saddle node bifurcation. Okay. So before that point, either there will be two or no equilibrium point, and after that point also there will be either two or no equilibrium point. And then there is Hopf bifurcation. That is very important and very famous also. Hopf bifurcation means the stability of the equilibrium point changes as the parameter changes. How? The stability changes from stable to unstable or unstable to stable, but it give rise as it changes its stability, is give rise to a stable equilibrium, a stable limit cycle, or a unstable limit cycle in the system as a solution. So in our case, there are two types of limit cycle that has been observed. That means we have observed stable limit cycles also and unstable limit cycles. Now in those cases, whenever there is a saddle node bifurcation and Hopf bifurcations, definitely most of the cases there will be another case that is called Bogdanov-Takens bifurcations. That means when at that time when both the bifurcations occur simultaneously. That means at what point saddle node bifurcations and Hopf bifurcations coincides, and it is a bifurcation of codimension 2. That means there are two parameters that has to be changed to obtain or to arrive at that bifurcation. Before that, all these three bifurcations, transcritical, saddle node, and Hopf, are all codimension 1 bifurcations. Then there is Boutin bifurcation. Boutin bifurcation means what? At that point where the Hopf bifurcating limit cycle is changing its stability. I already told that there can be stable limit cycles, there can be unstable limit cycles. So at that point when there will be we cannot say whether there is the limit cycle is stable or unstable. That means actually when there is a limit cycle, we check its stability by Lyapunov number. So if the Lyapunov first coefficient is negative, then it is stable. If that is positive, that is unstable. And whenever it is 0, at that point this Boutin bifurcation occurs. So in our model, all these bifurcations were obtained, and all these bifurcations were local bifurcations. But there is also another bifurcation, that is a global bifurcation, that is called homoclinic bifurcation of limit cycles. That means this limit cycle at a certain stage it disappears with certain bifurcations. So that bifurcation is called the homoclinic bifurcations, and that is a global bifurcations. And except transcritical, saddle node, homoclinic, and Hopf, these Bogdanov-Takens and Boutin bifurcations are two codimension 2 bifurcations. Okay. So now if we plot the curves related to those bifurcations in the parameter space alpha and beta, because alpha is the hunting cooperation, the parameter that is for hunting cooperation, and beta is for the alley effect. So if we just do this, we just draw all the curves on the face plane, then the parameter space is divided into 9 different regions. These regions are all topologically different. So that means in all the regions the solutions are topologically different. So mainly, so it is a very complex and diverse dynamics that we have obtained, and in each phase space, the solutions are qualitatively same or equivalent, you can say. So basically, if we go in the region R1, so I will just show one or two. I don't think I have much time left. So if I go in, suppose in the region R1, a general phase portrait will look like this. That means you can see whenever a solution starting from anywhere in the system in the phase plane with any initial condition it goes to the equilibrium point 1 0. That means the predator is going to extinction and the prey is actually sustaining at a constant rate 1. Okay, actually it is its carrying capacity. Similarly, if we go to a different region, we can see these things happen. And yeah, so this is in this case in the R4 region, you can see that there is a region, there is a local region such that the equilibrium point, interior equilibrium point, is stable. Each star is stable. So in that local region, wherever the solution starts from, it will reach to that interior equilibrium point, and that means what? That it is stable. And in this region, the population coexists. So that means in this region of the ecological region, whenever it starts, it will coexist. So in this way, also there are limit cycles. That means there will be periodic solutions, so they will converge on the periodic solutions. So in this way, what we can see is that if we go back and just note down the what are the qualitative dynamics of those different 9 planes, that is given by this. So that means what we actually observed is that in the parameter space. So if you see in a very uh, simple terms, if I need to say that if we start from any place in this parameter space, either it will go to the coexisting equilibrium point, or the system will go to extinction. Now you see this place in the that R5, R5, R6, these regions have different qualitative nature. So now if we increase the value of alpha, so the cooperation, if we increase the value of alpha in this region, that means in R5, so this red graph, if on the left of this red graph, as we increase the value of alpha, the system will be stable. That means the interior equilibrium point is stable here. So whatever so the effect of hunting cooperation, so the cooperation is actually here, it is enhancing the stability of the system. But on that way, if, conversely, if we increase the value of beta, that means alley effect, then it is actually taking the system to a extinction mode. So that means cooperation actually helping the system to coexist, but the effect of alley effect is actually making the system go to extinction. So that means we have to control this parameter in a proper way to make the system coexists. But in the works that was done before, in most of the system, they reported the case that the hunting cooperation only actually give rise to the case where the system coexists and it enhances the possibility of coexistence. But in our case, in our problem, actually, we have seen that in a generalized predator, with generalized predator, the ecological system actually
Jag
goes to
vet,
extinction,
men vad kan jag göra?
can go to extinction whenever we increase the value of L effect. So that
Jag
means
hör
L effect is always having an effect such that the system go to extinction. So my main observations are presented here, that the first observation is, of course, that the introduction of alley effect and the hunting cooperation is actually shows very rich dynamics with even with a very simple functional response, that is the type 1 functional response. Otherwise we cannot observe that thing. Secondly, incorporation of alley effect in our model,
Vad säger jag?
because of that complex dynamics, it enables us to model very different kind of systems or
Men ska
diverse
inte
kind of.
Abhishek göra det?
And thirdly, that it is that I already said that the alley effect is
Vad
very
ska jag
interesting.
säga?
Alley effect is actually having a destabilizing effect on the system. And as a result, what
Men
happens
hon kan
that
ju inte
hunting
sluta
also,
nu.
it is leading may lead the system to
Vad ska jag
coexistence, but
säga?
presence of alley effect, if the alley effect increases,
Hallå?
the system can
Hallå? Time is out.
Okay, so these are my
Oh,
references, and
no, you can
thank you for
continue
bearing
till the end. Yeah, thank you.
with me. Thanks a lot.
Thank you. And any comments or questions? Then we thank you very much and go to the next speaker. That is Dr. Poojas Basak. That is going to talk about the climatic predictability index for southwest monsoon season in a different district of West Bengal with application of fractal dimension analysis.
Good morning.
Good morning.
Good morning.
Yeah.
I'll now present. I am Dr. Piju. I will present my presentation about the southwest monsoon in India. So I will
Yes.
share my PPT.
Yeah, just one comment is we are little out of time, so please little bit hurry. We have to be little hurry. Okay, so
Okay, no problem, no problem.
yeah.
I'll give you the gist of the what I have done.
Sure, please.
Yes. Can I see everybody? I am audible and visible.
You are audible, but your screen is not visible.
You're
yet.
audible, but we can't see you.
Can't see you.
But we can hear you.
Okay. Well, maybe I am muted or what?
No, we can hear you, but you have to click on.
Your screen is not appearing. So can I am sharing? Sharing my PPT. Now, is it visible?
No, not yet. You have to click on the box. After sharing, you have to click on the box. Box of entire sharing or entire desktop, something like that.
Okay.
Then, yeah.
Okay. Now I'll share it. Okay. A desktop window. Screen sharing.
Yes, screen sharing.
And then I'll have to go my PPT to my PPT. So
No, it's not yet shared. You just enter screen, the leftmost box. Click on the leftmost box.
leftmost box. There is an open share tray. Is that okay?
Yes, first click on that open share tray.
Okay. Open share tray. And then there is a screen share.
Yes.
Okay. Then okay.
Click on that box.
Yes. Right. And then I'll click share.
Yes.
share, and then to my PPT. Not visible.
No, not yet.
Open to share. Share. Sharing your screen.
Sharing your screen, yes. You have to click on that box.
Uh, yeah, I have clicked my in my box. I have
I
clicked
think
in my book.
actually there are some problem. Maybe you can, I mean, he can leave and again join and it works sometimes.
Shall I leave
Yes.
and join?
Yeah, please leave. Then maybe we can start the next session, next speaker, and then maybe you would
Yes,
be the last one. Yeah.
yes.
Yeah.
And then we
Please leave and
call
join.
Dr.
Yes.
Kombina Rashai to talk about numerical solution for the 2 plus 1 dimensional partial differential equations via wavelet technique.
Am I audible?
Yes,
Yes, you are audible. Yeah, you are audible.
Am is my screen is visible to everyone?
Yes,
yes,
yes.
it's
Uh,
all
Yeah.
fine.
Thank you, because I am the last speaker. First of all, I thank to conference organizer for giving an opportunity to present my research work in this international conference. Myself, Kumbinder Saya from Department of Mathematics, Bangalore University, Bangalore. Today, I am going to present a paper entitled on numerical solution of differential equation via wavelet techniques. But actually, this is my outline, the abstract, introduction, so preliminaries of the Lagrange wavelets and function approximation, and some theorems on Lagrange wavelets, and what our proposed method, Lagrange wavelet method, and its application, conclusion, and reference. And here, so this is an abstract of our my presentation, today's presentation. Here, so we are proposing a new technique, which is a numerical technique to solve 2 plus 1 dimensional partial differential equations. We have chosen here the partial differential equation are in the form of Sokolov and Regular long wave equations, which is arranged in the fluid mechanics. Here we are solving these type of PDEs using the Lagrange wavelets via collocation method. So here we have solved some of the problems. First we proposed a method and then we solved some problems to find the efficiency of our proposed method. Basically here we are doing that, and the first whatever the PDE which are already modeled PDEs, we convert these PDE into system of algebraic equations by using the properties of the Lagrange wavelets. And after converting this system and solving by one of the methods such as Newton-Raphson method, we found Lagrange wavelet unknown coefficients and substitute those coefficients on the approximate solution, then it yields the Lagrange wavelets numerical based solution. So this is what we have planned to get a solution for any partial differential equation. And here we compared whatever the results got from our proposed method with other methods in the literature in terms of L2 and L infinity errors. So this is the introduction. But we have seen in the many real life situation can modeled into equations, even though it is yeah, either it may be ordinary differential equation, partial differential equation, fractional differential equation, and many more like this. But in the many of the especially in the field of fluid mechanics and chemical theory, mechanical biology, and biomodeling, many of the problems which is closely related to our real day-to-day life, they are modeled into partial differential. That is a partial differential including the non-linearity terms. So finding an exact solution for such a partial differential equation is not an easy task. So that's why so many researchers, that means mathematicians, switch over to the numerical techniques. But how we accept those numerical techniques? By those numerical techniques, we go for a solution for some partial differential equation which having a exact solution, and we compare those whatever the numerical solution obtained by the numerical methods, is it near to our exact solution. If it's very close, if suppose error is goes on decrease in power very near to zero, then we can accept those numerical method which can be applicable for the corresponding partial differential equations. So there are so that means already we have told that there is no, that means finding an exact solution for the PDE is not an easy task. Therefore there are almost no general technique that work for all such equations. So that's why we switch over to the numerical methods. So we have in many equations in engineering, physics and chemistry are modeled with partial differential equation with the non-linearity terms. So but we can test the numerical technique through the analytical solution of the nonlinear partial differential equation. Therefore, the many researchers are studying the numerical methods for solving such nonlinear PDEs. One of such PDEs are in this work we have chosen that the two-dimensional Sobolev and regularized long wave equations that commonly emerge in the flow of the fluids. So which explains the motion of waves in media. So the RLW, that means this RLW equations is the first introduced by the Peregrine to describe the development of the annula. Here we consider the 2 plus 1 dimensional Sobolev equation which is represented in the equation 1.1, and corresponding initial condition and boundary conditions are given here, where F denotes the non-linearity functions and alpha, beta, gamma, delta are the real constants, and remaining terms, which is capital F, G, H, are the real valued continuous functions. So in the equation 1.1, by giving the particular value for the alpha, beta, gamma, we are getting a corresponding types of partial differential. One is Sobolev, RLW equations. So for the equation 1.1, if we given alpha is equal to 1, beta is equal to -1, gamma is equal to 0, and delta is equal to 1, the obtained equation is nothing but a regularized long wave equation. And similarly, if alpha is equal to 1, beta is equal to -1, gamma is equal to -1, delta is equal to 0, then we got the equation is called as a Sobolev equation. And if we have seen the literature, many of the numerical methods applied for those such type of partial differential equation, they have mentioned here. That means Runge-Kutta method, split least square method, and similarly Galerkin method, etc. But here we applied a new method, which is, that means a Legoro wavelet method, collocation method. That is still, if you have seen in the literature, no one has solved this type of partial differential equation by using the Legoro wavelet collocation method. So that's why this impetus us to work to apply our numerical technique on such type of the partial differential equation. Before going to that, let's have a look on what do you mean by the wavelet. We know that the wavelet is nothing but a function. Instead of oscillating forever, it oscillates in the limited domain. That means this wavelet function generates a similar functions by using the translation and dilation. That corresponding function is called as a mother wavelet, and many of the mathematicians already worked on the wavelets, such as Morlet, Grossman, and Stromberg, Mayer, and Davacis. So and they proposed the one-dimensional wavelets such as a Haar wavelet, which is a discontinuous, Lagore wavelet, Legendre wavelets, and Hermite wavelet, and Chebyshev wavelets. They are all the one-dimensional wavelets which have a tremendous applications on the signal processing and in the applied mathematics field. And here the many such applications are as follows. That means the many of the in the literature already they have solved using the wavelet techniques of some different types of the problems, but not what we have finding a solution for the regularized wave equation. So these are the literature survey which is solved some equations using the wavelets techniques. And here, let's have a look on what do you mean by the definition of the Lagrange wavelet. Here, the equation 2.1 represents the definition of our Lagrange wavelet, which is represented as a theta n comma m into x. And these Lagrange wavelets generated by the Lagrange polynomial, which is given in the last equation. That means Lm plus 2 of x is equal to 2m plus 3 minus x into Lm plus 1 of x minus m plus 1 lm of x divided by m plus 2. By using these Lagrange polynomials, by substituting in the equation 2.1 and using these translation and dilation parameters, we get a corresponding wavelets in the limited domain. So this is my definition of the Lagrange wavelets. Here we have given this theorem. This theorem says that if suppose any solution of your partial differential equation, let's u of x comma y comma z is a continuous function defined on the Cartesian product of three unit intervals bounded by the positive real number. Then obviously, if we approximated such a type of bounded continuous function by the Lagrange wavelets expansion, then it is uniformly converges to the u of x comma y comma z. This actually says that that means it gives the bound for the whenever if we approximate, we get an unknown coefficient. For that unknown coefficient, this theorem says the bound. What will be the bound for those unknown coefficient to converge our approximation exactly for the u of x comma y comma z. And let's see, this is our proposed method. In this method, we have considered del square, that means a higher order derivatives we are approximating in the given equation 1.1. So similarly, the del cube u by del x square del t is my approximation by our Lagrange wavelets theta transpose of y k into theta of x. This is my approximation. Anyhow, the approximation of any function by infinite series, it is not an easy task. So that's why we truncate those equation. After truncating the given equation, we get a 4.1, and similarly the theta transpose of y represent this and theta of x represents this. Clearly k is represent a matrix. And now integrate equation 4.1 with respect to t from 0 to t, we get equation number 4.2. Similarly, once again integrate with respect to x, we get 4.3. And now integrate equation 4.3 with respect to x, we will get u is equal to u of 0 comma y comma t, which is represented in the equation 4.4. But in the given equation, it is not only initial value problem, also boundary values boundary conditions are also inbuilt in the given equation 1.1. So that's why we for applying the boundary conditions here we are using fitting b is equal to x in equation 4.4. If we fit b is equal to x in equation 4.4, obviously we get values for this, and then these whatever means del u of 0 comma y comma t by del x minus del u 0 comma y comma 0 by del x. Then substitute this equation in 4.5. This 4 substitute this 4.5 in 4.4 and 4.3. We get del u by del x. We get del u by del x, which is 4.6. Similarly 4.7. And now again differentiate with respect to t once 4.7. We get 4.8. With respect to y, we get 4.9. Differentiate 4.9 with respect to y, we get a del square u by del y square. Similarly with respect to t. So that means whatever in the equation 1.1, whatever the derivatives involved, we need to extract from we are going to be extracting those values from our proposed method. And then after that, now substitute equation 4.11, 4.10, 4.9, 4.8, 4.7, 4.6 and 4.2 in the given equation 1.1, and then collocate those equation by using the grid points. Xi is equal to ti is equal to yi. That means 2i minus 1 divided by 2 into 2 power k minus 1 into m whole square. If you collocate this, so we get a system of algebraic equation, which is a nonlinear algebraic equation, and solve this nonlinear algebraic equation by Newton's method. This yields our Lagrange wavelets unknown coefficients. It provides a Lagrange unknown coefficients. Okay, then substitute these unknown coefficients in 4.7, which is in terms of u of x comma y comma t. Then it will provide us the corresponding Lagrange numerical solution for general Sobolev and RLW equations. This is our method. Now, how this method applicable to our actual problems? So that's why we are moving to application section. That means here we are applying our proposed method on the some problem. That's 5.1 represents a given equation and initial and boundary conditions, and it has an exact solution, that is a u of x comma y comma t is nothing but sine pi x sine pi y into exponential of e power t. We solved by present method, and not only we have solved, we have compared these obtained results with other existing methods. That means the Hermite wavelet method, which is in the literature 50, and similarly Galerkin finite element method, which is in the literature 6. So we comparison in terms of L2 error and L infinity errors. Here it is a graph which graph 1 represents the graphical representation of the exact solution and numerical solution at different values of m and its absolute errors. Here this is our exact solution, and we solved this by at m is equal to 6 we get this, and m is equal to 9 we get this. At m is equal to 9, just have a look on, it is similar to our exact solution. So that's why, that means when m increases, the accuracy in the solution goes on increase. Similarly, it is the graph by fixing y is equal to 1 by 2 we have drawn. This is an exact solution, and this is my approximate solution at m is equal to 9, and it is corresponding absolute errors. And here is the one-dimensional representation. So by here I have fitted t is equal to 0, and I vary y on again this the x axis. So we got, means the slash lines are our approximation solution and dot lines are our exact solution. How close this? From this we can directly accept our method is very powerful. I mean, it yields very close solution to our exact solution. Here I have drawn graph. This is figure 4 represents what y is equal to 1 and vary t and x. We get a corresponding graphical nature of the solution. Here is the table 1 represents that means in here k is equal to 1, m is equal to 2. Our CPU time is 0.001, but our CPU time by the method in 30 0.023. That means time is also very less in our proposed method, but compared to 30, our literature 30, our method consumes less time. And if you move to the errors, this is a L infinity error by in the literature 4, and this is L infinity error in the literature 3. Comparing these two methods, our L infinity error is near to 0. This is x, that means exponential power minus 3. This is 2 and this is 2. So that's why our method faster converging than previous methods. That means literature 4 and 30. Similarly, this is a comparison of our L2 error. Our method yields more higher accuracy than the method in 30. Similarly, one more problem we have considered, which is a non-linear partial differential equation, and it has an exact solution. This, and again we solved by using our proposed method, and it is a graph. This is the graph for different values of t. T is equal to 0, t is equal to 4, and t is equal to 8. Similarly, t is equal to 12, t is equal to 16, and t is equal to 20. This is our approximate solution. And next, this is a table which is represented by fixing t is equal to 10 and t is equal to 2 for different values of k. K is also varying and m is also varying. Just why we are using the wavelet techniques means, when k as well as m goes on vary, we get a higher accuracy. That's why we are using the wavelet techniques. Here we have compared with the CPU time literature in the 30. So if we have a look on this fourth column, this is a CPU time by the method in the 30, and this is a CPU time in our proposed method. So comparing these two, our method our methods consumes less time. Okay, less time is also very important. And in the observation of L2 and infinity error compared to this previous method, our method yielding a higher accuracy. So from this, we can directly assume that our method is best method and comparing to other methods. And here is the final my conclusion. Here we have proposed our Lego wavelets method by using the properties of the wavelets such as orthogonality and compactly supported and vanishing moments and smoothness of the properties of the Lego wavelets. We have solved this problem and compared our obtained results with the other methods, which is in the 6 and 30 in terms of yield and infinity error. And our method solved by the using the software MATLAB, and it consumes a less time compared to other methods. So that's why we can, and also we can solve some more types of the partial differential equation with slight changes in the proposed method. This is our today's presentation. This is my references. So thank you one and all. Hello. Hello.
Yeah, Lena, I think you were muted. So could you please unmute yourself, Lena?
Hello. Am I audible, sir?
Yes, okay.
I stopped sharing my.
But the one that didn't get in, what's to do with him? Hello.
Hello.
Hello. The next speaker was Dr. Pijas Basak.
Yes, I am here.
Yes.
I'll just share my. Yeah, I'll try to share it because last time I again re-entered, and so.
And you are going to talk about climatic predictability index for southwest monsoon season in different districts of West Bengal.
Visible? Is it my visible?
Yes.
Is it visible?
Yes, now.
Oh,
Yes.
I have cleared out the problem. So this is climatic predictability in southwest monsoon in different districts of West Bengal with application of fractal dimension analysis. So actually I am concentrated on the particular region of India, that is West Bengal state, and within India, in the east side of the India. Actually, I cannot complete the work for the other state and other regions. So this is the application of fractal dynamics. Some districts of West Bengal have shown different characteristic. This I want to discuss. So this I have some found out with the. This is from fractal analysis. So there is a rainfall type, the effect of moderate rainfall, a lot of agriculture, effect of moderate is a lot of agriculture, but effect of dark rainfall, it means and again drought and excess rainfall. This is flood. That is for definition purpose. So my region is within India, state, and there are different districts. There are 18 districts in West Bengal. So each of the districts has been different characteristic. That is my topic. Overview of the region is 88,072 square kilometer. Mean rainfall is 106.93 centimeter, and standard deviation 10.27. These are the statistical measures. Skewness is almost normal. Kurtosis is skewed. Next is the fluctuation of climatic series of temperature, vapor pressure, and rainfall over time and space. Actually, the variation, they're very closely related to two climatological series, that is temperature and vapor pressure. They are very close to the rainfall, and that fluctuate temporarily, that is from time to time, that is month to month, day to day, etc., etc., and also from place to place, that is region to region, and month to month, season to season. The fluctuation is of two types: temporal and and temporal and spatial. The seasons for the study. Actually, what I have projected here is the four seasons available in India. That is also it is valid in the in West Bengal state also. That is pre-monsoon rainfall, March to May, southwest monsoon rainfall June to September, northeast monsoon rainfall October to December. These are the three seasons of rainfall we study. And will be compared with the vapor pressure and temperature. The dynamics is a very good, very known dynamics of constellation in India is has a direct role from Indian Ocean, that is the convection coming from the Indian Ocean, Bay of Bengal, and this is rainfall falls in every part of the India, especially in the southwest monsoon. Southwest monsoon means June to September, there are massive rainfall in east part of the India, where in northeast monsoon, the rainfall is in the south of India. But we are concentrated on the districts of West Bengal. So we are only studying the southwest rainfall occurs, but not always in the same kind every year. Sometime it is good rainfall, sometime it is flood, sometime it is drought. It depends on, because the temporal variation is there, and research has been done by the following researchers. So that is Chandrendra, Hastendra, and Garcia, and for different regions. Northeast region, Mohapatra, Karnataka, Iyengar, West Bengal and Assam has been studied by myself, Basar. What is the objective of this study? Why should I study fractal dimension and all these things? This is the objective, that is southwest monsoon is dependent on climate dynamics. West Bengal is sensitive to classical monsoon rainfall. Southwest monsoon is linked to the existence of vapor pressure, temperature, humidity, convection, and other factors also. Rainfall is related to various causes: vapor pressure, temperature, humidity, convection, and others. Out of them, vapor pressure and temperature are very close to the southwest monsoon rainfall, as research follows. Several remarkable attempts were taken by the other researchers, that is Parthasarathi and Dwarikar, Kripalini, Rangarajan, and Sant, and they wanted to link the temperature and vapor pressure with the rainfall, but all at all India level. Nobody has studied this. Not adequate attention is provided for the leakage of temperature and vapor pressure with southwest monsoon in West Bengal. So in the current analysis, with the study the temperature and vapor pressure and precipitation time series and the area of the heart of the classical monsoon and sensitive to monsoon fluctuation. Fractal dynamics always expected to yield some insight. We have seen the papers I have mentioned that fractal dimension in climatological series, fractal dimension gives some insight how this a series is occurring or what is going to occur in the next time. Like in the current paper we have done this. How fractal dimension is found out. Fractal dimension is found out basically we have found out that fractal dimension is 2 minus h, where h stands for Hurst exponent. The Hurst exponent is h, and if we compute the Hurst exponent, we can find the fractal dimension with the relation formula. It is discovered by Voss in 1985. So how to find out the Hurst exponent? I'll discuss after a little bit.
Hello. Yes,
1 minute, because what happens when dimension is 1.5? So the interpretation of fractal dimension is, if I suppose the fractal dimension is 1.5, then what should I say about the rainfall? I can say there is no correlation between amplitude between the successive intervals. That means no trend in amplitude in that distant series, and the process is completely unpredictable. If fractal dimension is 1.5, then the full series is unpredictable. We cannot predict anything. Suppose I predict 5, it will be 7. So completely unpredictable. If fractal dimension is going towards 1, then it is predictable. And as if it is a persistence meaning that the increasing or decreasing tendency will be follow increasing or decreasing tendency in future. Supposing that in 2 days the rainfall is increasing in somewhere when fractal dimension 1, then in the future years the rainfall will be increasing or decreasing in future. Presently it is increasing decreasing means future it is increasing decreasing if fractal dimension is going towards 1. Instead, if fractal dimension going towards from 1.5 to 2, 1.5 is the basic point, no correlation and unpredictable. If it is 1.5 to 2, then it is anti-persistent character. That means increasing or decreasing tendency in today's will be decreasing or increasing tendency in future. Today, suppose it is increasing tendency, in future it will be decreasing tendency. This is it happens when fractal dimension is comes near 2. So in geophysical time series, fractal dimension plays a very good role in towards the nature of the series. This is the mechanism to find out the Hurst scale analysis series that is discovered by Mandelbrot and Wallis 1968-69 in 2 papers. He has elaborated how to find out the Hurst exponent series. That is, if x1, x2, xn is a series time series, then r by s is called Hurst exponent, and it is calculated in the following fashion. Mean value is calculated 1 by n sigma 1 by 1 to n xi. It is everybody knows to it. Then sorry, and then we find out the adjusted series, that yt, that is equal to xt minus m, and then cumulative derivative of the series, that is zt, is equal to 1 by n into sigma I is equal to 1 to t yi. It is called cumulative derivative series z. Then risk-scale rain series is calculated as RT is equal to maximum of Z1, Z2 up to ZT minus minimum of Z1, Z2 up to ZT. And its standard deviation is ST is equal to, as per the standard deviation formula, root over 1 by T sigma I is equal to 1 to N xi minus U whole square, T is equal to 1 to N. And the risk scale series is R by S, suffix T means at time T, is actually Hurst found out that, assume that this R by risk scale series is follows exponential time function. He assumed that, and that has been explained very much by Mandelbrot and Wallis, that Hurst time series, risk scale series is an exponential series. So that is equal to, assumption is that it may not be exponential, but assumption is it is exponential. And we find out the following graphs of the sum of the districts, that is called Bankura district. So this is the Hurst risk scale series, blue line, and this is the time series fitting, that is linear series fitting, and that is the slope of this line is Hurst exponent. That is, actually it is invisible, 0.3425, because I had to accommodate this small space. And this is why this is the for the fitting of the line, and its slope is the Hurst exponent. This is for temperature. This is second one is for vapor pressure, and third one for rainfall. And this is for the district of Bankura. This is for the district of Howrah. Actually, there are 18 districts. I had provided only 4 of them because of the, if I show you all the graphs on time will kill. So Malda district, and this is for Darjeeling district. In Darjeeling district, first exponent is very high. Anyway, the construction of that I have told, construction of Hurst exponent. After we construct the Hurst exponent, we find out the fractal dimension d is equal to 2 minus h as per Gauss. The fractal dimension, now we write fractal dimension of temperature is dt, and fractal dimension of fractal dimension of temperature is dt, and Hurst exponent of temperature is ht. And then we find out the index. This is called temperature index. I have found out is 2 times modulus of dt minus 1.5. And similarly, the fractal dimension of vapor pressure is dp because it is pressure, and Hurst exponent of vapor pressure is hp, and thus vapor pressure index is PIP is 2 modulus of dp minus 1. So to keep the parity, I have noted down PIT means temperature index, PIP means pressure index. Similarly, rainfall, this is PIR. These are the 3 indices, one for temperature, another for vapor pressure, and the third one is for the rainfall. After we find out we project as predictability index. We construct the predictability index as PI is equal to PIP, PIP, PIR. This is a predictability index which combines all the predictability. First one is for predictability. Second one for vapor pressure predictability, and third one is for rainfall predictivity. So we want to keep them under one shadow so that after looking into the predictability index as a whole, first one is temperature, second one is pressure, vapor pressure, and third one is for rainfall, we immediately come to understand the index is low or high, low or high. Suppose this temperature is low, vapor pressure and rainfall may be high. So immediately we can find out from this picture what is the predictability of such a district. And if it is true that if it is close to 1, the process is very much predictable. If the index is very close to 1, that means it is very much prone to the predictable. And if the index is near 0 or almost 0, then no predictability. This is why, okay. And second one is this, that if the predictability is same thing, only for vapor pressure. If it is nearly 1, that is very much predictable, very good predictability. And if it is nearly 0, it is almost no predictability. So from this index, we understand the predictability of the following fields or series. One main point, we note that PIT, PIP, and PIR are the amount, not the amount of temperature or vapor pressure or precipitation. These are not amounts. This is only how the precipitation, temperature, and vapor pressure changes from year to year. This is not the amount. This predictability is not the amount of the pressure temperature, but this is.
Sorry, time.
Yes, within 2 minutes, this only final result I'll put. So this is the way we find out, and then we have found out for districts the predictability index of temperature, vapor pressure, and rainfall, and written down as a whole bracket. Okay, so these are the result inspect and had studied. So we have come to these are the other districts. All the districts we have found out. So the ultimate result I will show you that one thing we have found out how can you tell it that it is very much predictable. So some convention is there. Convention is from the other researchers that if the predictability index is greater than 0.4, it is should be strongly predictable. If the predictability index is between 1.5, 0.1 and 0.4, it is weakly predictable. And if the predictability index is less than 0.1, it is not predictable, and we denote it by N. So we denote it by S, W, and N. With strong predictability, index is greater than 0.4, and weakly predictable, that is the index is between 0.1 and 0.4, and not predictable if index is less than 0.1. And then these are the result. For Darjeeling district, we have a unique result that temperature index is weak and pressure index and rainfall index is strong. That is, can be predicted. Strong means it can be predicted very well, and weak means can be predicted, but some doubts may be there. And of course, the other districts, Kujbihar and Jalpaiguri districts, they have this type of index we have found, that is temperature and rainfall has weakly predictable, but vapor pressure is strongly predictable. This is the pattern of Kujbihar and Jalpaiguri. The pattern of Purulia, Murshidabad, Kolkata, Midnapur, and Howrah. So all this is no predictability at all. So suppose I take the temperature series of Howrah, and we ultimately get no, it is not predictable at all. Uncertainty, full of uncertainty. So if I want to say next year it will be 5, it will be 11, like that. So there is no such predictability down in the three: temperature, pressure, and rainfall. And for Purulia, Murshidabad, Kolkata, Midnapur, and Howrah, same thing. And other results are Malda, Birbhum, Bardhaman, Kolkata, Uttar Dinajpur, and Dakshin Dinajpur. They have weak predictability in temperature and vapor pressure, but very strong predictability in rainfall. Another result, Bankura and North 24 Pargona. This is temperature is completely unpredictable. Vapor pressure is completely unpredictable because index is less than 0.1 and rainfall is weakly predictable. Prediction in these two districts is very difficult, Bankura and 24 Pargana. And Hooghly, Nodia and 24 Parganas had three different characteristics. That is weak, unpredictable, weak. This is for Hooghly. For Nodia, unpredictable, weak, weak. And for 24 Parganas, weak, weak, unpredictable. So this is the conclusion. That with the help of the predictability index, we can find out the predictability, and farmers also maybe depend on it because they want to know what is the rainfall probability or what is the rainfall index.
We are little out of time. So
Okay,
could you please?
it's almost 10. Almost 10, no problem. So this is the conclusion that we cannot apply this such and such application for the modeling purpose. First is predictable, then you can model, right? Okay. So conclusion, this predictive index can be useful when developing climatic model of a region. First we see the predictive index, then we have to model it. All these things, with looking into the index, we can say it can be modeled or not. So data has been just sincerely taken from National Data Center, Pune, for monthly data of West Bengal. And these are the references. And thank you very much.
And thank you very much for a very interesting talk.
If it is interesting, all right. So only mathematics and statistics is applied. That's all.
Thank you.
Thank you. Thank you very much.
And this ends this session.
Thank you, Lena, Dr. Lena
Yes.
Trell, for chairing this session. And thanks to all the speakers of this session, as well as the parallel session that was going on. And now it's ended up. So we thank to all the speakers of both the sessions, as well as both the session chairs for chairing this session. We are running out of time. So without having any time or delay, it's our great pleasure to switch over to the next session. And may I now request Professor Eric Trell, to please share your screen. Professor Trell, can you hear me?
Oh yes. Hello, Abhishek.
Yes. Can you share your screen, please?
Yes, we should do that.
Yes, and after that. Okay, maybe before that, yes, before that, I think it's my great pleasure to introduce Professor Eric Trell. Yes, let me first introduce Professor Eric Trell. Maybe you can, could you please just Remove your screen then it would be easier for me. Yes. Yeah. Yes. Thank you. Thank you very much.
Yes.
It's my great pleasure to introduce Professor Eric Trell. Professor Eric Trell, MD, PhD, is an emeritus professor, Faculty of Health Sciences, University of Linköping, Sweden. He is a physician, health promoter, and scientist. So in short, we can say he is a scientist as well as a doctor. He has published more than 400 medical papers, book chapters, lecture articles. His mathematical and physical studies started in around 1970s and are directed to algebraic structures and structural deviation of the elementary particles and periodic table symmetries following the original works of Sophus Lie, the founder of the Lie theory. He has done collaborative research works with the scientists from Norway, England, Russia, Nigeria, and India. He has written more than 40 papers on mathematical physics. Most importantly, he is the founder, vice president of IMBIC. He is the director of Sweden branch of IMBIC. And one thing we should know that he was the former vice president of Calcutta Mathematical Society. So we can understand that how involved he is with IMBIC according to his biodata as well as his work both in the field of medical sciences as well as in the field of mathematical physics. So without having any delay, it's my great pleasure to welcome Professor Eric Trell. Now it's yours.
Thank you. Thank you. Now we shall take this one. Yes. Yes.
Yes, it's coming.
Vet jag inte verkar den. Nu fungerar inte musen. Den har låst sig. Fråga, säg att vi inte kan höra.
It seems to have been locked in some way.
Locked? No, you're not locked. What it is saying?
Säg att det snurrar en symbol.
No.
Nu ska vi se.
Men då är ju jag kommer.
Yes, so we can see your screen, so it's already there. So please open your presentation maybe, or you have only selected, yes, I think you have only not the whole screen, that's why. Maybe could you, yes, we can see your screen now. Yes, can you open your presentation now? I think you have chosen not the entire screen, maybe. That's why.
But you have you can see my screen now.
Yes, the screen which has my image and all, not the presentation.
Ska vi se, och då får vi ta här dela och sen då är det den då. Och då är det
yes, now it's something English.
Pappa, där.
Yeah, it's coming. Yes.
Coming. Fine. I thank you to my daughter.
Yes.
Because my daughter solved this problem. Anyhow, I shall try to catch up those fumbling 5 minutes by talking rather fast. And I think the title of the presentation
please take your time. Yeah, that's 40 minutes each.
Thank you.
Yes.
Well,
Okay.
it's called Game of Lee Cellular Automaton, and I refer here to the Game of Life, of course. Cellular Automaton is a kind of system, graphical or other, that repeats itself. So, in this case, I apply it to the elementary particles and above all the atomic and periodic system symmetries. And although it will turn out to be rather regular geometric figures, one could say they are also quantum superpositions and a kind of marginal accretion of quantum superpositions, because the atoms, the elementary particles, molecules, and whatever, they are very closely entangled and has to be treated as units. But that doesn't exclude that they are composed. So I go on with my presentation here, and we can say that Marius Sophus Lie and Mendeleev are quite closely related, and their basic work were produced in 1869 and 1871 respectively, and thus in next year there would be a 150-year anniversary of Marius Sophus Lie. So what did they do? Well, I can say that both didn't deal with particles. Particles is a later invention as applied to the atoms and so forth. But they were applying kind of more phenomena. Lie, for instance, was dealing with a phase transition between Euclidean space, which is straight line space, and transferring this to the sphere. And this was his contribution. He invented spherical geometry, actually. A lot of other things also, differential equations and infinitesimal transformations. But they are all quite ordinary geometrical structures from the start. And we can say that the machinery of Lie algebras, it occurs not on the surface of the respective forms, but in the interstice between them. So there happens a phase transition, and you can say that the phase transition is the subject of Lie groups and algebras. And they are not particularly complicated, but they were when they were invented. And that is the kind of perspective that we often lack when we think that these things are self-evident. They were there from the beginning, but they were not. And when they were invented, it was a big step of humanity in transferring plane, straight line surfaces to spherical ones. And of course, that's very important nowadays when you shall faithfully, from the start, translate flat maps to spherical ones. It's the same principle, but in the Lie case, it's done by infinitesimal transformations. I think the figures are self-explanatory, or at least explaining them better than I. So I just move on and conclude that the commutation relations of the Lie algebras, they are represented by what we call commutation or root space diagrams. And they were invented by Killing in a couple of years later than Lie. And the tendency has been more and more not to treat them just as representation, but as real things. Because if you have an algebra that is made of lines, and they are represented by straight lines, of course it's the straight lines that makes the thing. And thus we often notice that they lead to lattice structures. But the complication of A2 diagram, which is SU3 over the complex numbers, is that the kind of lattices they do, they are always flat. They don't have another dimension. So what's actually representing SU3 is A3, which is a duplicated A2 diagram. And you can see they then span the sphere, and they are to be regarded as the infinitesimal generators of the sphere. And in that angle that we can recognize in a way as a kind of partially commutating but still diagonal generators, and standing in that relation to the straight spherical Euclidean sphere infinitesimal generators, which are the x, y, z axis, of course. I come back to this, but now we just state that SU3 is made in its realization over the real space, which involves a duplication in comparison with the complex space. It's made by the root space diagram invented by Killing. And then, of course, now we have a kind of a cell that generates something. And that is the meaning of, you can say, cellular automaton. Repeated applications of this cell that contains the essential generators of a geometry that can be then studied by repeated applications of itself and see where it leads. So the standard model, that is a majestic model. It's very true, but it rests upon Gell-Mann's concept of rotations of point-like particles. Particles didn't exist in that, so to say, use when Lee and Mendeleev worked. But, okay, rotating particles, and particles, they are quarks, they are gluons, they are electrons and whatsoever. Although they are amorphic, their rotations have ability to express the symmetries you see. But it's very complicated structures, of course, and they are really fantastic inventions. No doubt about that. But Lee's ground element was a disturbance or something. Need some kind of disturbance. That's something that can be, yes. Okay, Lee's ground element was the straight line, but it was not whatsoever line. It was of length equaling 0. And the straight line of length equaling 0, of course, is equally small as an infinitesimal sphere, but it has the ability to connect. So in practice, it works like an infinitesimal generator or actually a partial derivative. And if you just use them directly as infinitesimal generators of, so to say, connections, they are in fact differential equations in nature. And by this invention and identification, Lee actually founded the whole chapter of differential equations as one part of his gigantic production. However, using the length equaling 0 directly in concatenations, he obtained all kinds of transformations. Translation, rotation, helical harmonics, and so forth and so on. And what he is doing actually is operating in tangential space, because his lines are tangential because they operate in the interstice between cubical and spherical geometry. So they form a tangential space. And we see here that the root space vectors, if we consider them so, they are actually tangentially spanned over the surface of the unit sphere, here shown in half size. And if you take and make steps of these root space vectors, they will project a kind of transformation of the sphere if you, from the endpoint, again connect them with the sphere or other focal points of the ground sphere. And then you get the kind of elementary particle transformations that form the supermultiplet transformations of Gell-Mann. And you can see what kind of structures you end up with by just operating with the root space vectors and their steps. And you can see that you calculate the major semi-axis and the minor semi-axis. And the mass, of course, according to the quark pressure formula, would be inversely proportional to the minor semi-axis. And you just have this simple calculation. You get exact replications of the elementary particle masses. So this is the interior aspect of the cellular automaton. And the mesons, they have SU2 times U1 symmetry. And if you calculate them according to the differential volumes, you get also very close replications to the basic. And you can go on and go on. These are the differences, you could say, between various transformations, both between mesons and between baryons. And this network, it is not only diagonally extended, but you find also some connections which are extended 180 degrees and 90 degrees towards each other. And these form orbit, and these orbits go in this way and represent, of course, the muon, which calculated according to the length in relation to the proton radius, closely correspond to those measures. But if you try to connect the diagonal vectors, you can't get an orbit over the surface, but you get a tripled kind of structure here. And if you work a bit upon the purely geometrical volumes of that, you end up with the tau symmetries. I don't go further into this, but you can also go to the leptons, which are always generated as the final outlet of baryons via mesons, or in this case, muon, and coming out as rays, as it were. And you often notice then that they come in by polar symmetry. I just rushed through this and again say that now we have been over the surface, we have been in the interior, but now we go out of these root space vector, and we said that they could create a lattice. So what we will do in the continuation will be only to deal with the lattice, outside lattice, and connect it with the atomic structures and with the periodic table, again as quantum superpositions, because those blocks that you can find here created by a system, they are actually quantum. So if you start building with this generated by themselves lattice elements, you find that they create what we call an isotropic vector matrix. And that is constituted by space filling 1 octahedron, 2 tetrahedron, and they are dual to the cube, you can say. And they are the only straight kind of solid that really packs space. But we can immediately recognize that this vector here, this matrix here, this is, of course, continuous. It's always separated. And you can see that this kind of lattice would actually be able to fill space. But how to find a kind of continuous path which didn't cross itself? And then we come to the next thing here, that according to Schrödinger equation, we must establish a kind of wave packet. we must in some way lodge the continuation of the lattice into Euclidean space. And that we have to do by identifying packable Euclidean space, you could say, structures guiding them. And we can call them chaperone modules. And these are then, we can call them qubits. These are wrappings of the interior SU3 formula, because what we generate in this way is a real R3 times SU3 wave packet, but in the solid state configuration space and always very faithful to their parents. If you look at the connections from the SO3, the wave equation form, we can see that they form kind of geodesics here. And the interesting thing is that you knock out one of these, they are entangled because there are two rule space vector actually forming one geodesics. So this is the mechanism and basis of entanglement. Anyhow, we go back to the packing here, and we see that the module here, this one, which is the kind of ordering of a continuous packing, it really can be tessellated itself. And here just shown how it forms a rhomboid structure with a central hole, and that's interesting. And if we take and store them together, they tessellate space, but they have some defects and gaps between them. So we need to find a kind of accommodation, and we see that this ground module here is insufficient to pack space vertically. It needs a roof, and if we construct a roof, just making a cap of it, this will add some extra such qubits, and if we count them, they are 153 in the bottom plate, 153 in the cap. What? Some comment? No? Okay. Well, anyhow, this cap would have this structure then, because it adds this column and then it tessellates completely densely the space. And it's possible to magnify this and see that the central hole is preserved. But in order to continue over space, one has to add an extra, and that was this extra column. And then you find that this kind of realization really obliterates space. So that can be useful in some end stages of evolution, but they would be in a way obstructing their tessellation. But we can show them what they would look. We have the ground module here. It's a very simple structure, and we have the roof, and then we combine the ground with the roof, and we get a combined module here, which we could compare with a ribosome, a translation apparatus of biology, because between them they transcite real forms. And we can see here how these modules combine then and come together and form two varieties of packing, one with a central hole, which is essential, one without a central hole, which is also in a way essential. But they, in turn, can be packed. And but as I mentioned, not coming any further. So we have to find an alternative, and then we shall let two such modules collide tangentially and like separate into two halves. And we find that the one half shown here has this symmetry again. And it can be combined in the same way. And we have the kind of no-hole combination that would just pass on translationally. But we can also, by a little twist here, make them combine with a central hole. And I show some hopefully self-explanatory variation of this. And we see that it's a combined structure if we take the kind of just packet, then it would form the neutron in the constellation. And if we take just SO3, and together they will form what we can call helium, deuterium, and if it turns around, it will form helium. So now I think, but it's essential to remind that it's a three-dimensional structure. It's not like, for instance, graphene is often illustrated as some kind of central points, which are supposed to be the atoms. And then there are big bars here, supposed to be the bindings, whatever they are, and like holes in between them. So it's a kind of paradox, you could say. And in fact, how does a crystal looks like? For instance, a hexagonal crystal on the infinitesimal scale. Yes, it's a kind of solid structure that has a flat roof and flat bottom. Just as a notation here. But if we go on with these combinatoric games of quanta, because these are quanta, we see that we have one form of this modular lattice, which is the package, and that is have no other structure, as it were. So it's neutral, you could say, and it's forming the neutron. Then we have the SO3 variety, and we know that that contains also small units. And this we can call then for the hydrogen. And this is the protium form of hydrogen. But if we combine it with the neutron packet, it gets hydrogen 2, deuterium. And then we can see what happens if we take this package and put it upon deuterium in this case. Well, it has the same volume and same form, so it would be spatially packable, but it lacks the kind of charge, and it will become tritium, that is 1 loaded and 2 unloaded components. So we have that kind of arithmetics, you could say, that 1 plus 1 is 4, which we have here, because we have, for instance, if we put just an SO3 on top of the deuterium, we get 2 helium-3. But if we turn both around themselves and pack them to protium, 2 deuteriums, we got the helium structure. So this is the game, and this is the game of Lie, you could say, in its external variety. And we see that they pack very good, these are helium, these are alpha blocks, you could say, and they pack space with a kind of twist, and they are getting a bit complicated to put together in this LIGO variety over all space. The bigger they become, the more complicated would be this Lego kind of game. So we create what we call Duplo bricks of helium, or we call Duplo bricks of the SO3 and Duplo bricks of the neutron and Duplo bricks of another structure. But we can see that if you put a deuterium on top of a helium, we get 3 lithium-6. And if we just take protium and pack upon it, we got 3 lithium-5. And if you pack a neutron upon a helium, we got 2 helium-5. And it's that funny arithmetics that, in a way, is duplicated, although being singular. But that is the only way of solving these tricky equations of the periodic table. And we can see how the representation is made. We have the singlet packet cell, which is forming a neutron, and we have the Doppler variety of this. And we see that if you combine 2 of these singlet cells, they just come upon each other and get the same form, same volume as the helium, but only half the mass, because it lacks that mass that, after all, the deuterium also adds to. And we have the singlet coil of SO3 here, and we can see that continuation of its geodesics here creates gammas and neutrinos. And I think the mechanism of neutrinos and gammas are just splitting up kind of such structures. And that goes also here in that we also have creation of neutrons, but not of gammas, of course, from the singlet cells of the walls. And we have protium, and that is represented as this. And if you try to put 2 neutron in equiposition, that won't go because they won't pack upon each other. But if they are very, very much forcefully screwed, one of them will transform, and it just goes about sending out some gammas and neutrons, and it's squeezed into a deuterium. And that is the combined wall and wave structure, which is the concrete R3 times SO3 wave packet, which is typical of real space, because this is Euclidean and this is more like a wave. So deuterium here is so represented. Yes, we go on. And now we can just continue the game, and we pack lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, and they look quite funny, I would say. But if we take the singular representation, the Doppler representation, they are a bit more simple, and we see that they are packing together very nicely in space. These are the, so to say, oxidation states, and we see that oxidation states, namely the positions that can be offering bindings to molecule formation, is like this. And so when we come to higher structures, we need more complex. So the most stable isotopes of sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon. But argon 36, this is the astrophysical variety. It's the most common in the cosmic perspective, but not in real conditions here on Earth, because they are formed by decay. Anyhow, we see that sometimes we have to include a neutron in order to find the best shape. So this is the mechanism of neutrons, you could say, that they are needed to buffer, you could say, form variations, because everything in this game is about packing space-fillingly quanta as superpositions. And that is how actually atoms are constructed, even quantum mechanically. And we can go on with Doplos here. This is potassium. This is calcium 40, 20 calcium 40. This is, by the way, the heaviest isotope that has no neutrons. But then if we go further with scandium and tin and vanadium and chromium and magnesium and up to iron, this kind of Duplo stapling applies. But after iron, it doesn't apply anymore because then the burning processes are. But up till then, at least, the kind of Duplo game here is very productive. It combines molecules. And here we have potassium with +1 and chlorine with -1. And they form salt, of course, in 2 varieties. And we can have carbon here, which is, of course, very reactive because it has plenty of binding sites. And together with chlorine, it will become carbon tetrachloride. In 2 also various ways. And we have titanium tetrachloride and so on and so on. But we can say that Duplo bricklaying, they include both male and female binding opportunities. And they need the space they have. And thus, with bigger and bigger atoms, more and more possibilities emerge, but they are always marginal. They are on the surface, in the outer layer. We can see some processes here just very rapidly that this system reflects a lot of processes. Carbon burning, for instance, and there are various varieties of carbon burning. We have neon burning generating, and we have oxygen burning. And now we have so big molecules that's actually meaningful to have Duplo representation. We have other oxygen burning, say, with silicon burning. And we can also, in the laboratory, make things that the stars don't do. And for instance, alpha shine, we just add alphas and we build up neutron-less isotopes. And we can reflect other beta chains, for instance, which I will come back to, so I don't show them, but that is things that we can do. And it starts to be complicated when we have come to iron, because the Duplos really don't suffice in covering the corners and so on and so on. So the real remaining representation here is triplos. And triplos, of course, they have the same rules as, but they are more adequate in terms of morphology, you could say. So if we repeat potassium to iron with triplos, you can see it's a marginal accretion of elements that occupy new layers. And you can say that each generation, each period in the periodic system is a new layer of, and now we are in the 3rd layer and also in the 3rd period. And the colors here, by the way, they are only made here for some kind of evidence, but also because they are the colors of the respective noble gas in each period. But we see that they are packable and come together, and we have the triplo bricks here. And after iron, the kind of construction of these elements, they have to be done by slow neutron capture and then come rapid neutron capture. Anyhow, it's a trick of, so to say, transforming superfluous neutrons to deuterium and then alpha bricks. And this is by the process, as I showed you, that if they are pressed, so to say, against ipsilateral wall element, it's transforming to the next higher. For instance, krypton here, I show you because it's so symmetric. By the neutron capture, becomes rubidium, and it has the same mass because it adds the mass here, but it has the same form and the same atomic number. It has one more atomic number, of course, by that. Yes, I go on. Then, of course, we need a lot of neutrons because virtually all future nucleosynthesis is by neutrons. And I show here two processes which are used to create neutrons. And they are coming from the interior of stars in various formations. But the rest of the game, now very rapidly presented, is to build up layer after layer of this marginal accretion of quantum superpositions, because these triplets, they are actually quanta. And we can also see that they offer both him and her kind of binding opportunities. And that is a kind that you can, in a way, repeat differentially. But just going on with marginal building here, we go over the fourth period here, and we can see that I showed you the alpha, the beta decay routes by the arrows. And we can do it in different ways. And I come to the summary of the fifth period, or the fourth period. And here we have period 1, the central helium. We have, and we have neon, and we have argon, and now we have krypton. So, and they fill, so to say, a cubical marginal allocation. And we can compare with the real periodic table, and we see that when we come further in periods, it goes well here, but coming to 6 and 7, we have the problem of the lanthanides. Anyhow, all of these things that we are going to see are space filling. They are constructed to fulfill a kind of parallel epiped geometry. And the way to space fill them is sometimes by inversion and gluing them together, and otherwise, if they have very symmetrical forms, just putting them together, and thus making the representation wider. So we go from krypton and continue to xenon all the way by systematic one-step refigurations and additions to the formal structure. And we also see that we got the isotope. It just has to do with how many neutrons we have. We can remove neutrons, we can add, and they will represent the whole isotope spectrum over the whole actually observed range. But if we come to xenon, we can represent it like this, or we can represent it like this, with duplets in this case for simplicity. And then we can see that this fills the fifth period. And then we come to the sixth period and the seventh period. And now I just rapid go on here. And the problems with the lanthanides, for instance, that we have 12 extra things that doesn't fit into the ordinary periodic table, that is solved here because now we have such a wide margin that it's only to pack and lanthanides starting here and just continue. And what are the lanthanides do? Yeah, they are packing internal subshells, so they are not interfering very much with the external surface, and thus they are very similar. All lanthanides are similar because they have equally much oxygenation and so forth size, and thus fulfill their pattern all over the periodic table. We go on here, and it's many now, it's 32, so we have to come far away. Yeah, we come to gold. Gold is very interesting because now it has filled the O shell, and it's very stable, it's very symmetric. So gold is characterized by big stability. So we shall see. Takes a bit of time for the apparatus. Yes, now we come from gold to radon, and radon fulfills the 7th period, and of course can be packed like all others. And now I'm afraid it's a bit slow, but now we come to the 7th period. And now we have come to a point in the periodic system when the formation is reverse. It's very often going from heavier states to the gold. Should come. Yes, organism, and now it jumped for joy away from organism, which is the real goal of the thing. Organism, gold. This organism, that is the heaviest documented atom, and really the rally ended there. This is organism 294, and it's very symmetric. It's got fills, subshells in all dimensions. You can see here. This is organism. This is where you come by this route, and back in the far left corner, and yes. Yeah, it's a bit more complex than the problem. Now we have to turn back again. But I'm aware now we can see how it looks. Finally, I hope it's resting. Yeah, here we have organism. So it's not only speculator. I think it was made altogether 5 or 6 atoms of organism, but it was the conclusion of a very logical scheme, and it is possible to regenerate them in reality, at least this real kind of representation, and it does very, very heavily comply with the real structures. And we can even show that you can have isomers of it, which is observed in reality also. And interestingly enough, you can start building on organism, putting, for instance, a neutron here. Then you have the outset of a union enzium, speculated first atom in the 8 round. And then you can build on the 8 round, and you can get the end state of the 8 round also by this method. These are still not produced, but there is space for them, because if you make an analysis of how the ground modules pack the consecutive periods in themselves, it's absolutely predicting how they will pack in a kind of tangential plane representation of its 3-dimensional packing order, not pecking order, but packing order. And Thus, we have still a margin for expansions of the system. But as I mentioned in the start, it's really interesting that we have a kind of dummy, we have a kind of model instead of module, a model, a toy model, as Penrose have called them, where we can sit and do some manipulations and explorations and investigate molecular and other properties. And one very strong point of it is the isotope spectrum that can be, so to say, caught by the cell mechanism and pattern. So I stopped by references, and I hope I didn't took too much time. And well, thank you.
Thank you, Eric, for your colorful presentation as usual. It's a nice presentation. So any comments or questions or remarks? So you are all welcome to unmute yourself and ask questions if you would like. Or if you have any further question, you can send him email to eric.trell@gmail.com. So Eric, erik.trell@gmail.com. So if you have any further questions or queries, you can send him directly email, or you can ask any question or comments if you like. Okay, so if there is no such questions or queries, let's thank the speaker once again. Thank you, Eric, for
Thank
your
you.
nice talk.
Yes.
Yes. Now it's my great pleasure. So, Eric, could you please stop presenting? Maybe.
Yes.
Yeah.
No, it stopped. Yes, fine.
Thank you. Okay. It's my great pleasure to welcome our next speaker. There is a catch here. So the next speaker would be Professor Rogero Maria Santilli, who was born and educated in Italy, where he achieved his PhD degree. He acted as a chair in nuclear physics at the Avogadro Institute in Turin. In 1967, Santilli was invited by the University of Miami in Florida to conduct research for NASA. In 1968, he joined as a faculty to the Boston University, where he taught physics and applied mathematics. During 1975 to 1977, he went to MIT, and from 1978 to 1983, he was as a member of Harvard University. Santilli is the author of more than 250 technical articles and 180 post-PhD level monographs in mathematics, physics, cosmology, superconductivity, chemistry, and biology. He has been recommended by scholars around the world for nominating him for the Nobel Prize in physics as well as chemistry. But unfortunately, due to his emergency meetings and all, he couldn't attend us, he couldn't join us. But we are fortunate, and he is kind enough to send us a video recording of his talk. So let me play his talk so that we can enjoy his talk. So let me share my screen and yeah, can you see?
Yes, we can see.
Okay. Let me play. Okay, just a minute. I need to add the audio as well. So I have to again. Yes, otherwise you can see, but you cannot get the sound.
Maria Santilli. I would like to thank all distinguished speakers all participants and all organizers of this important conference. In my lecture, I would like to present certain historical aspects underlying the famous argument by Einstein, Podolsky, and Rosen, according to which, quote, quantum mechanics is not a complete theory, end of quote. I believe that a knowledge of the historical background is important to have an in-depth knowledge of the famous EPR argument. So let's begin our lecture. Let's go back to Germany in 1935, in which, as we all unfortunately know, the Nazi had reached the peak of their military as well as political power. But what a number of scholars do not emphasize sufficiently well is that the Nazi had reached the peak of their scientific power. The reason is that quantum mechanics is a theory that was conceived, structured, and developed by German scientists. Here we have on the left Max Planck, and in the middle Erwin Schrödinger, the originator of the famous Schrödinger equation. And on the right we have Werner Heisenberg, the originator of this famous time evolution with the Lie algebra structure. In 1935, three then unknown Jewish immigrants from Europe, Albert and Rosen, had the courage of opposing the Nazi in the peak of their scientific power by stating quantum mechanics is expected to need a completion, namely broadening, a generalization. This conference has been organized to honor the memory of Albert Einstein, Boris Podolsky, and Nathan Rosen for their courage that they showed in 1935, a time in which America had no military power as yet. Not now, of course, thanks God. Indeed, their paper is absolutely inspiring, and I recommend it to all scholars, but not done so, to read it. The first statement is very well known and says, quote, quantum mechanics, and we are now quantum chemistry, are not complete theories. End of quote. What does it mean? It means that quantum mechanics, quantum chemistry are a magnificent theory. They work very well in certain conditions, but not necessarily so for under sufficiently broader conditions. The second statement is very deep for quantum chemistry because it states that the wave function of Schrödinger equation cannot represent the entire physical and chemical reality. Indeed, it's very easy to see that the Schrödinger equation for the two identical electrons of a valence bond predicts a repulsion with the ensuing lack of a quantitative representation of a molecular structure at this moment in time of the 21st century. The last statement is also extremely well known, is by Albert Einstein, quote, God does not play dice with universe, end of quote. Einstein was attacked for this statement from all corners, even dubbed as a crackpot. But let's think about with our own mind. There is no doubt that a proton in empty space verifies Heisenberg uncertainty principle. Period. This is experimentally verified. But let's think in different physical conditions, such as illustrated in this picture, a proton in the core of a star. That proton, ladies and gentlemen, is exposed to extreme pressure from all possible directions. It is then very plausible to expect that the uncertainty of this proton in the core of a star have to be different than the uncertainty of the same proton when it's freed to move in all directions in empty space. The EPR paper was attacked from the entire scientific community immediately following its appearance. Here we show one of the most vociferous opposition, that by Niels Bohr, the head of the Copenhagen interpretation of quantum mechanics. I studied this paper when I was during my graduate studies at the University of Torino in Italy, but I was baffled because Niels Bohr does not address the point. The point is that Einstein does not state that quantum mechanics is wrong. No, he cannot state that. It just states, Einstein states that there may be conditions under which quantum mechanics is inapplicable and therefore it needs a completion. Now, because of this virulent opposition to Einstein that lasted the rest of his life, Niels Bohr was dubbed to be an anti-Semitic. However, I don't think this dubbing applies to Niels Bohr because his wife was Jewish. Also, Niels Bohr, many Jewish physicists escaped the Nazi and emigrated to the United States. So the issue which is on the table is why Niels Bohr was so adamant against Einstein. It is my opinion that Niels Bohr acting that way because of the power of the Nazi of the time. After Niels Bohr, there were a flurry of so many I cannot quote them all here. I want to quote only a paper by J.S. Bell, who states that a set of quantum mechanical particles having spin 1/2 cannot admit a classical counterpart. I did spend time to prove that this statement is correct. It's because known from famous Bell's inequality. I proved that it is correct, but under the silent, tacit assumption, which are for point particles in empty space, which is necessary for which assumptions are necessary for the very formulation of the axiom of quantum mechanics and this mathematical elaboration. And in fact, the moment we will see that the moment you consider different physical conditions, such as extended particles within hyperdense physical medium, Bell's inequality cannot even be formulated, let alone disproved. No, it becomes inapplicable. And any statement that Bell's inequality is wrong would be unethical. In conclusion, as a result of the Nazi pressure, the quantum mechanics was initially established worldwide. Then money came into the picture to reach the current situation in which the governmental agency throughout the world, they disperse billions, if not trillions of
I think the sound is not coming.
Hello? Hello?
the combustion of fossil fuel, uranium type of iron. What do we see? We see an irreversible process, namely a process whose time reversal image violates causality, because it will imply that the smoke has to reconstruct the coal with the violation of a number of physical law, let alone common sense. When exposed to this process, I was told that the irreversibility is in reality illusory, because when irreversible processes such as this combustion are reduced to elementary constituents, then quantum mechanics is recovered in full. This view that was indicated to me back in the mid-60s is still widely adopted in the physics community. With all due respect to my teacher, that would like to honor to this day. And indeed, I prove a number of so-called no reductions. One of them states that the macroscopic, irreversible system cannot distantly decompose into a finite number of elementary particles, all define quantum mechanics and related conservation laws. Vice versa, elementary particles verifying quantum mechanics cannot reconstruct a macroscopic irreversible system under the correspondence or any other principle. The origin of this theorem is essentially due to the time reversibility of Heisenberg equation, Heisenberg time evolution, if you want, of an observer A, which is characterized by the which is entering in the A and the Hamiltonian A. Technically, we'll say that the Lie bracket are invariant on anti-hermeticity, and therefore can represent the time evolution of the Hamiltonian is identically null. That cannot be otherwise. I life in trying to represent irreversible system via quantum mechanics and failed. So therefore, I reached a point in which I decided to dedicate the rest of my life to complete quantum mechanics and honor Einstein, Podolsky, and Rosen. And that's exactly what I've done since my graduate studies. I initiated my study by going back to the founder of analytic mechanics, Giovanni Lagrange, who was born in Torino and wrote most of his paper in Italian, that they are French or maybe other languages. In studying the original paper written by Lagrange in Italian, I was shocked to see the substantial difference between the Lagrange equation that I was studying in the graduate school, which are here depicted here on the top, and equations which are down here. What are the differences? The equation on the top can only represent conservative system and with axiomatic potential interactions that are well known to be reversible over time. But in reality, instead, the Lagrange introduced in his equation this quantity which he called an external term, and non-conservation as well as irreversibility. Hamilton from England, who followed Lagrange, presented this equation also with external terms that you can see here depicted at the bottom of this slide. Again, the entirety of the physics literature, let's say the primary physics literature of the 20th century, all quotes an equation without external terms, and they are
লিঙ্কে গন্ডগোল হচ্ছে।
Just hitting it to
allow quantitative representation of the irreversible process. I spent about a year of my life in mathematics library in Europe to look for such an algebra defined by mathematicians. I locate one dimension is a mixture which is defined by American mathematician Albert without ever during the set. The once identified correct definition with all the basic action, the realization, and I published my thesis in the Il Nuovo Italian Fisico. This paper colleague completion of quantum mechanics according to Einstein, Podolsky, and Rosen, because jointly with the completion of Lie algebra into this jointly Lie admissible, the order admissible algebra, introduce specific realism of Heisenberg time evolution. While being at Harvard, in late 1978, I published Springer Verlag 2 monographs under the title Foundation of Theoretical Mechanics, which had been written during my stay at MIT from 1974 to 1977, following the Volume 1 in the left identifies the ultimate limits of representational capability.
Hello. Hello.
legacy. The reason for my uneasiness is that I never accepted quantum mechanics as being a final theory for nuclear structure since the time of my graduate studies at University of Torino, because quantum mechanics has been unable to achieve an exact representation of the experimental data, which is the deuteron, with embarrassing deviation from the prediction of the theory from experimental data for heavier nuclei such as zirconium. Here is an illustration of this very important aspect. As we all know, representation of the magnetic moment of the deuteron, despite all conceivably possible corrections, including quarks and quantum field theory and many other attempts, there still remains a 1% unresolved representation. Next, there is a mystery in nuclear physics that has baffled me and a number of other colleagues, namely the neutron, we all know, is unstable in nature, yet when it is combined with a proton, it becomes permanently stable. Well, it is my view that until we understand this mechanism, which is not even addressed by quantum mechanics, our knowledge of nuclear structure will be limited. But was baffled by the representation by the spin 1 of the deuteron. According to the basic axioms of quantum mechanics, particles with spin 1/2, such as proton and neutron, can only couple in a stable way in singlet, resulting in 0 total angular momentum, while the deuteron has spin 1. Well, in order to maintain quantum mechanics, then nuclear physicists consider a collection of states, the ground state, as well as excited states, and in this way they do indeed achieve angular momentum 1. But to be physicists, we have to admit reality. A deuteron, when it's isolated in vacuum, it is in the ground state with spin 1. That is the physical reality we have to address. I completed my stay at MIT by writing a number of papers on the integrability conditions for the existence of Lagrangian and Hamiltonian, published under my affiliation to MIT, as well as preparing the draft of 2 volumes of Foundations of Theoretical Mechanics that were released at MIT preprint. I would like to add that my work on the completion of quantum mechanics was still extremely immature in 1974. And I simply did not have the courage to address such distinguished colleagues and tell them what at that time were essentially my personal dream. And so in September 1977, I left MIT to join Harvard University under a grant from the Department of Energy. A few days following my arrival at Harvard, I was called by the DOE with a request that I should try to investigate some basically new, out-of-the-box possibility of achieving in the future the controlled nuclear fusion. I told the officer that that is a magnificent task. Definitely, yes, I am interested, but at one condition, however, that I had first to understand the most fundamental fusion in nature, which is essentially the fusion of the hydrogen atom into the neutron in the core of star. As soon as I initiated to study this problem, I immediately recognized that the synthesis of the neutron from the hydrogen atom simply cannot be quantitatively described by quantum mechanics for a variety of technical reasons. The most important one being that the mass of the neutron is bigger than the sum of the mass of the proton and the electron, as a result of which, in the event you want to use a Schrödinger equation, you have to use a positive potential energy, and you have to come up with mass excess. Those aspects are simply anathema for quantum mechanics. So this aspect essentially sealed in my mind the absolute necessity of following Einstein, Podolsky, Rosen teaching that there exists indeed conditions in the universe for which quantum mechanics has to be completed. These results were published in this Harvard paper, carries my affiliation at the Lyman Laboratory of Physics of 1978. The moment I decided to complete quantum mechanics, I immediately went back to the founders of our knowledge, as I usually do. I rarely study their followers, because only by studying the originator you see their intuition and their view. And in fact, I immediately discovered from Enrico Fermi that he believed, quote, that the usual concept of geometry not necessarily apply in the interior of strongly interacting particle, end of quote. This means that a structural generalization is needed in Fermi's view for the structure of the hadrons, meson, and baryons. Also, then I went to Blatt and Weisskopf, who wrote justly celebrated excellent book in nuclear physics, and they state very clear, it is possible that the intrinsic magnetic moment of a nucleon, when in close proximity with another nucleon, is different than the corresponding value in vacuum. Thus, this historical account sets clearly the target, namely to achieve an invariant representation of extended particles under condition of mutual entanglement, penetration with other, which therefore ensuing most general conceivable interaction, which are generally called of nonlinear, non-local, and non-Hamiltonian character, according to the conception of the nucleus depicted in this figure, which is according to experimental data. Indeed, if you compare the volume of nucleons with respect to the nuclear volume, you will see the nuclear are partially in a condition of mutual penetration. By contrast, quantum mechanics will only allow me the conception of a nucleus here on the left, namely an ideal sphere with the isolated point in it. There is no question I recognize the historical value of quantum mechanics as an approximate description of nuclei. After all, nuclear power plants, they do work. So we have to admit the historical character, but this is not the point in this lecture. This lecture is to look at the future, so that the human knowledge can advance. Once the problem was identified, I immediately went through all the libraries of the Cantabrician area, including, of course, Harvard and MIT and Brandeis. I also consulted a number of mathematical luminaries in the area that were indeed, there are great mathematicians in the area. And that's why I asked them the question, I need to represent proton and neutron as extended, therefore deformable. What kind of mathematics can I use? And therefore had to be built. So I went to work. And I was moved from the Lyman Laboratory of Physics to the Department of Mathematics at Harvard University. The first thing I did was to generalize Einstein's language, which was a complete, conventional associative product among two arbitrary quantity, matrix, function, number, etc., into this form here, which is axiom preserved, namely the product to the right is still associative, but nevertheless is broader because it contains in a matrix an operator T called the isotopic element, which has an arbitrary functional dependence and is only restricted by the condition of being bigger than 0. Following the introduction of this associative preserving process, also called isoproduct, it was immediately possible to introduce a representation of the nuclear structure that I was looking for, namely as a collection of extended, generally non-spherical and deformable proton as represented by this space term, the fourth term being representing the density, plus an exponential part which represents all expected non-linear, non-local, and non-potential interaction. And this is exactly what I was looking for. But I immediately realized that by generalizing the product, ladies and gentlemen, that I had to generalize the totality of applied mathematics that I've been studying all my life. The first was a mandatory generalization of Lie algebra, which I did immediately following the introduction of the isoproduct. I did it in the second volume of Foundational Theoretical Mechanics, where you can find an isotopic lifting or completion, if you want, of all aspects of the Lie algebra, including enveloping algebra, Lie group, transformation theory, etc. After that, a number of distinguished mathematicians work in the field. Should in particular mention Professor Grigorio Tsagas of the University of Thessaloniki in Greece, who wrote a book entitled Santilli Isotopic Algebras. And then I discovered that this was not enough, because the unit of a numeric field used throughout the 20th century, which is the number 1, is not conserved by the time evolution of this theory because it is non-unitary. Therefore, this theory, to achieve consistency, this theory requires new number, had to be formulated in new number and cannot be formulated on over conventional number. After spending years of trial and error, finally I had the courage of asking the question whether the abstract axiom of a numeric field do indeed admit some new realization or not. Once I had that courage, the answer was yes. And indeed, it came out that the axiom of a numeric field do not necessarily require that the basic multiplicative unit is the number 1. No, it can be an arbitrary quantity, provided that it is positive, definitely. In this way, I introduce the so-called isonumbers, which are depicted here, that also stimulate a number of mathematical work, including a monograph by the Chinese mathematician Yang, entitled Santilli Isonumber Theory. So this new mathematics that became known as isomathematics started to have some momentum, but I still was missing the fundamental issue, namely the capability of maintaining over time the deformed character of the extended proton and neutron. So I spent years looking everywhere for any possible insufficiency with no result. Finally, I had the courage of addressing the real limitation of quantum mechanics, which is given by Newton differential calculus. Why so? Because Newton differential calculus can only be defined to a finite number of isolated points, and with ensuing necessary condition of representing particles as point light. Some of my colleagues disagreed with me, said, no, Newton differential calculus belongs to Newtonian mechanics. I respect their view, but I disagree, because look at the Schrödinger equation, Heisenberg equation. They are defined by the Newton differential calculus. So until that the differentials and the derivative appearing in those equations are broadened from their current old definition only at isolated point to definition in volume recovered by the particle, then quantum mechanics cannot be consistently completed. This was my view at the time. It is my view now. Finally, in 1995, I had the second courage of addressing Newton differential calculus, asking the question whether the axiom of this calculus admits some kind of degree of freedom. And the answer was yes. And the abstract axiom of Newton differential calculus do not require that the multiplicative unit has to be the trivial number 1, but can be an arbitrary positive definite quantity, which can also depend on the local variable of differentiation. This was the birth of the isodifferential calculus, which is at the ultimate foundation, because the representation of extended particles within physical media starts here. I published the isodifferential calculus in 1996 at the Rendiconti Circolo Matematico Palermo. I remember that my wife and I made a trip, Tampa, Palermo, Tampa, for one specific reason, to say thank you to the editor, Professor Vitro, for publishing what appears to be my most important paper, the paper on the generalization of differential calculus from its definition to point to its definition to volume representing extended particles. Many years later, the mathematician finally discovered this new calculus, and there's been a flurry of activity. I have to mention here Professor Svetlin Georgia, who has written not 1, 2, 3, no, has written 5 volumes in the isodifferential calculus, which are published and are available from Nova academic publishers. Following the achievement of maturity, and only following the achievement of maturity, the corresponding formulation or completion of quantum mechanics into the Lie isotopic branch of hadronic mechanics, also called isomechanics, was essentially elementary. And that's basically you replace every product, conventional product, with an isoproduct, and you get the new mechanics. And the new mechanics can be obtained by non-unitary transformation of quantum mechanics. So it's very simple to construct against the rather widespread belief that Santil is doing complex mathematics. No. All our physical models can be constructed by a method known to a first-year graduate student, namely because you mainly have to use non-unitary transform of established quantum mechanical procedures. There is one point, however, that has quite some deep connection and implication, and it is given by the realization of the linear momentum, which is compatible with the rest of the formulation in isomechanics. To understand this implication, colleagues should know that by 1994, we still did not have a completion of quantum mechanics that was sufficiently mature for application and experimental verification. Why so? Because we missed a consistent realization of the linear momentum. And lacking the linear momentum, I didn't know how to construct the angular momentum. I was frozen. And why the difficulty? Well, because it turned out that the reason for the inconsistency is because all realization in isomechanics of the linear momentum via use of Newton differential calculus turned out to be inconsistent. So the realization of the linear momentum in hadronic mechanics is the most compelling evidence on the need to generalize Newton differential calculus, under which the transition from points to particle to extended particle may eventually result to be a dream, but not a scientific reality. Most importantly, I will recommend to note the commutation of isocommutation of coordinates in isospace, but the coordinates do not commute when projected in conventional space, thus illustrating the deep nonlinearity of the theory, even too linear at the higher level of isospaces over isofield. Following the achievement of maturity in isomathematics first and then in isomechanics, there were a flurry of application, experimental verification, industrial applications. But I plunged myself in what was my original aim back in the mid-1960s during my graduate studies at the University of Torino, namely prove that the Einstein vision on the lack of completion of quantum mechanics was indeed plausible and significant for advancement of human knowledge. And therefore, I went immediately to use the formalism for the first proof of the EPR argument. At that time, I was a guest of the Joint Institute for Nuclear Research in Dubna, Russia. Thanks to such a gracious hospitality, in 1994, I wrote in Dubna this paper that was submitted to Acta Applicanda Mathematica in 1994. Eventually published in 1998, following 4 years of grueling referee review, but eventually it was published. What does this paper say? Well, this paper first shows that the ISO product permits an instantaneous, concrete and explicit realization of hidden variables via this determinant for the case of spin 1/2, 2 dimension, for the case of which is realized for the form which is realized here. And this realization of the hidden variable persists even when you assume that the isotopic element is 1. So once the hidden variable were no longer hidden, but were realized explicitly in a concrete matrix way, everything was consequential. You do the map of the poly matrices, they're called the poly-Santilli isomatrix. Since the transformation is non-unitary, you can be sure that the structure constant and the eigenvalue are the same. Yet you recompute Bell's expression and you clearly see that there's a large multiple, that the new expression, the hadronic expression, is thanks to this hidden variable, is a large multiple of Bell's inequality. So therefore, a system of extended particles within in condition of deep mutual penetration or entanglement does indeed admit, according to this theory, a classical counterpart, but therefore proving Einstein's first legacy. Following the publication of the paper at Acta Applicanda Mathematica, I somewhat abandoned my old aim of proving Einstein legacy because of virtually complete lack of interest by the scientific community, except, as I indicated earlier, a few luminaries that indeed can change the history of science. And they pushed me that, Ruggero, you got to complete your task. So I went back to work years later, and in December 2019, I published at Ratio Mathematica this paper that essentially proves perhaps the most important part of Einstein's legacy, namely the plausibility of Einstein determinism. Let's review this very, very quickly. Those are the uncertainty of quantum mechanics, extremely well known. You recompute everything under isotopy. It's a rather elementary calculation. And you see that the standard deviations in isomechanics are proportional to the absolute value of the isotopic element T. But the isotopic element T is extremely small for any interior system of extended particle in condition of mutual penetration, and in particular that this isotopic element tends to the value of the isotopic element tend to 0 under gravitational collapse. So in this way, both the product of the standard deviation as well as them individually, they will tend to 0 with the decrease of the value of the isotopic element. So to prove Einstein intuition, I basically recall Schwarzschild metric. I decompose Schwarzschild metric into the product of the isotopic element multiplied by conventional Minkowski metric. I assume identically for the isotopic element, the space part, we are doing only a space theory here, so I assume the space part of the isotopic element, and then it was elementary to show that the limit of the standard product of the standard deviation within the gravitational collapse tend to 0, by therefore recovering Einstein determinism. The number of applications of isomathematics are just too many to be listed here. It includes theoretical, mathematical, and scientific, as well as industrial, a number of industrial applications. I just want to mention I did achieve an exact representation of all characteristics of the neutron in its synthesis from the hydrogen atom, both at the non-relativistic and at the relativistic level. but only thanks to the completion of quantum mechanics into hadronic mechanics. One point of curiosity, so to say, but also significant, colleagues should know that I could only publish the results in Russia at the Joint Institute for Nuclear Research, thus illustrating my appreciation to Russian colleagues. And this was done via the Joint Institute released a communication on my results. But the results were then published in China, but it was impossible to publish these results in the United States of America, England, or Italy. Notice that each of those papers achieved a numerically exact representation of nuclear magnetic moment for the first time in history. Despite that, papers were rejected. Besides a very significant number of applications, development, above all experimental verifications of the formalism in various branches, such as, for instance, for the behavior of the mean life of unstable particle with speed, Bose-Einstein correlation. I would recommend the interested author to consult my 3 volumes of Element of Hadronic Mechanics. I would like now to outline the third problem in mathematics and physics that requires an apparent mandatory completion of quantum mechanics in order to achieve a quantitative treatment of the problem considered. This third problem deals with the ultimate and most fundamental problem of chemistry, which is molecular structure. With a clear, repeated admission and recollection that quantum chemistry has indeed achieved absolutely historical advances in human knowledge throughout since its inception, allow me to admit that I never considered quantum chemistry to be the final theory for chemistry. The reason was, and it is now, that quantum chemistry still misses a quantitative model representing the valence bond in a way consistent with experimental evidence. In fact, if you consult the most advanced available treatises in quantum chemistry, you will see here that, for instance, the water molecule is represented like this with little legs, joining hydrogen and oxygen. And but essentially, the bond between the hydrogen and hydrogen is a nomenclature because it misses the attractive force, because it misses an equation representing the bond between the valence electron of the hydrogen and the corresponding valence electron of the oxygen. The reason for my reservation regarding the lack of final character of quantum chemistry, and therefore the needs for its completion, goes back to my graduate studies, because it's very easy to see that the Schrödinger equation for the 2 valence electrons of a molecular bond, those electrons, they repel each other. You need a positive potential energy here because electrons have the same charge. Then you do a little calculation and you can easily see that the 2 electrons are repelled with a force of the order of 230 newtons. This is an astronomically big repulsive force. I cannot have peace in my mind until at least I try to solve this problem. And indeed, it was only thanks to the investment by the financial community that invested significant funds in Gas Corporation. Then I had all the means to study this problem in the early and mid 2000. And it was a relatively, at that time, it was a relatively possible, I don't want to use the word easy, it was possible to show that indeed the completion of this basic equation into the corresponding equation of hadronic mechanics or isomechanics, which is essentially requires intermission of here, in this product of the isotopic island and the use of the isodifferential calculus, then this lifting of this completion does indeed allow the achievement for the first time in my knowledge of an attractive, not only an attractive force between the 2 electrons, but a strongly attractive force represented by the Alton potential. I should stress that by no means the electrons in the valence bond are identical to the electron in vacuum, ladies and gentlemen. This conception is outside physical and chemical reality. It turned out that the electron in valence bond, they are extremely intermingled in a very complex way with non-linear, non-local, and non-Hamiltonian interaction. So an attractive force is indeed possible because of the mutation, completion, if you want, of their structure, resulting in a problem that perhaps is one of the most interesting problems that I have addressed in my life. I published the results in this volume, A Foundation of Hadronic Chemistry, published in 2001. And then, thanks to the collaboration by Don Shillady, a chemist of Virginia Commonwealth University, whose collaboration I still honor me, and I still have no words to express my appreciation. With his collaboration, we proved that this new strong valence bond allows, apparently for the first time, the achievement of an numerical exact to the desired decimal representation of the characteristic of the hydrogen molecule in this paper and the water molecule in this second paper. In my paper published in December 2019, Ratio Mathematica, I have shown the plausibility of Einstein determinism for extended, therefore, deformable particles in the interior of gravitational collapse. We should also recall that the majority of the scientific community nowadays accepts the lack of validity of quantum mechanics in the interior of a black hole due to the extreme density exists locally in such areas. Despite all that, the data elaboration of the totality of high energy scattering experiment conducted at CERN, Fermilab, and other particle physics laboratory around the world said data elaboration is done by the use of quantum mechanics, despite the fact that the scattering region achieved nowadays have a density comparable to that in the interior of a black hole. This occurrence established the societal, let alone the scientific need of due scientific process on Einstein's important view that quantum mechanics is not a complete theory, namely is not a theory that can describe the entirety of all possible conditions existing throughout the universe. Additionally, in 3/4 of a century, we have been unable to achieve the controlled nuclear fusion despite the investment of billions of dollars of taxpayers' money. In this lecture, we have shown that quantum mechanics is not expected to be exactly valid for nuclear fusion because of its strictly irreversible character, while quantum mechanics is strictly reversible over time. Moreover, we have shown that the addition of contribution from irreversibility implies rather major engineering implementation. This is a second case illustrating the importance of due scientific process on Einstein's view that quantum mechanics is not a complete theory. Finally, during the past century, quantum chemistry has been unable to achieve a clean combustion of fossil fuels with the ensuing environmental problems that are now affecting the entirety of human society. In this lecture, we have shown that a reason for this insufficiency is the lack in quantum chemistry of a quantitative representation of molecular structures, because the two identical electrons of a valence bond are expected to repel each other, according to the Coulomb law we have studied since high school. In this lecture, we also shown that quantum chemistry cannot possibly provide a consistent representation of energy-releasing chemical reactions because the latter are irreversible over time, while quantum chemistry is strictly reversible over time since it is based on quantum axioms. In this lecture, we've also shown that, by using a suitable completion of quantum chemistry, there is a realistic possibility of achieving indeed an attractive force between identical valence electrons under their suitable entanglement, as well as to achieve a consistent representation of energy releasing, therefore irreversible chemical reactions. This is a third clear example of the societal, let alone the scientific value that after about 1 century of oblivion, the scientific community finally implements due scientific process as well as scientific democracy on Einstein's important legacy that quantum mechanics is not a complete theory. In conclusion, I believe that the scientific community is facing the following alternative. On one side, the continued sole use of quantum mechanics for whatever condition exists throughout the universe in complete oblivion of Einstein's legacy may eventually imply a scientific obscurantism of historical proportion. By contrast, the proper implementation of due scientific process and serious scientific democracy on Einstein's legacy may well allow mankind to reach the stars within a few generations. Thank you for your attention.
Okay. Hello. Yes. So that's the end of his session. So now we'd like to go directly to the next session. So if you have any question or comments, you can send email to Professor Santilli. Yeah, so if you have any comments, or you can send us email so that we can directly forward to him. And without having any delay, let us directly go to the next session. Professor Shuit Dey.
Can you see me? Hello?
Yes, I can hear you. Yeah.
You can hear me? Okay.
Yes.
You can see me?
Not yet. Can you
Now
present your screen? Yes.
We can see you, but not your screen.
Yes.
Professor Dey.
What is my hello?
Yes.
Can you see me?
Yes, we can see you. Yes.
Can you hear me?
Yes, we can hear you.
Of course you do. Yes. First, I must tell you, I thoroughly enjoyed the lecture of Professor Santilli. Extremely interesting. And tell him that we have an article which appeared in the Letters in Applied Mathematics in 1998 with regard to communication between two elements in nature in a quantum state. We brought certain ideas very similar to what Dr. Santilli said today. I enjoyed it very much. Please communicate this with Professor Santilli and send me his email address that I can communicate directly.
Sure.
Can you
I
hear
will surely. Yes, I will surely send you.
Okay, now what you want me to do? Go back to my presentation?
Yes.
Okay. Can you see that?
Not yet.
Can you see now? Abhishek?
No.
But it's over there. It says it's here.
Is it shared? Can anybody else see this?
Okay, let me see whether it is. Wait a minute. I think
you have to press on the box and arrow.
Which box? I do not see any box.
And
let's go back to the. Okay,
yes, I think.
Right here. Which box? Right here? Oh, yes.
The
And then I will share
and
right here.
yes, then you have to press on the desktop or share screen.
Share.
Yes, I think. Yes, it's coming. Yeah. Yes.
Can, now I'm sharing.
Yes. Now I can see my face on your screen. Yes. So you can start your presentation then. Yeah.
Can you see this?
Yes, yes, yes. It's visible now.
Can you
Thank
see
you.
this?
Yes. Yes, yes.
You can see.
Yeah.
Everybody can see.
A mathematical approach on the studies of mRNA.
Corrections
Yes,
required
yes.
by
Correction request by
COVID-19
COVID-19
vaccine.
vaccine. Yes.
Clear?
Yes. So let me introduce a bit you. It's my great pleasure to introduce Professor Shuhit Dey, who is currently emeritus professor at the mathematics department of Eastern Illinois University, USA. He is a former senior research associated with the NASA, and he has plenty of papers on mathematical biology. Now, currently, he is working with Corona and all, and we are very much eager to hear from you, sir. So please continue.
My colleague is my son, Charlie Day. He is the Director of Professional Development and Training of Texas Advanced Computing Center at the University of Texas in Austin. Let me go straight to the heart of the problem. I first express my deepest condolence to all the people who lost their loved ones during this pandemic. We are fighting a disease which our body, as we understand, never ever experienced. It is called SARS COVID 19, meaning severe acute respiratory syndrome. This corona means crowned viral disease discovered in 2019. It is an RNA virus that we all possibly know, which means its genetic information is stored in the form of RNA. It is highly contagious, causes acute respiratory distress syndrome, and it is extremely fatal. And what information I got so far shows that even it is apparently cured, the residues could be life threatening in the long term. And I'll explain that later. The reason is this may not be applicable to the younger generation, but I'm an old man, and this is possibly strongly applicable for the people whose immune system is getting poorer. We will study this mathematically, and it's a very preliminary work, and I'll appreciate after my lecture is over if somebody sends me some valuable information with regard to this particular vaccine. First, I'll show you exactly how COVID-19 attacks us. This is the lungs that you can see, and here is the picture. These are the alveolus, and this is the infected lungs. Right here, we see the infections, and these are the alveoli. These are very small balloons. And when we breathe in, alveoli swell, and when we breathe out, it contracts. Now, COVID-19 virus enters through mouth or through nose. According to my ENT physician, very young man, as we understand, ENT means ear, nose, and throat, which means possibly it also enters through our ear. This is the crowned virus, the COVID virus. They enter and they go straight through our bronchial tube, because right here is the, let me go back to the next slide. This tonsil. Let me show you what that I mean. Right here you can see this is the body. Here is the tonsil. Tonsil is the first line of defense in the body. That means the coronavirus, somehow or other, they put tonsil under control in order to go all the way to the lungs and affect the lungs. And I want to show you two things, two organs. The tonsil is here and the thymus is here. And I must tell you what this thymus is. We all have this thymus. Many doctors believe that if you talk to a doctor, the thymus dies around the age 45. We do not believe that, and we have concrete examples, and I will refer to my book, which is forthcoming, on battling breast cancer through novel mathematical and computational studies. Anyway, let me go back here. And coronavirus enters, goes all the way to the lungs. And all around the lungs, right here you see the alveoles, we have got certain receptors called the AC2 and CD147. They go they get attached. When they get attached, that means the proteins that they release, they get attached right here, and then they enter inside the lungs. And here is the picture here, that this is COVID coming, and you see this spike protein, this spike, and this is the cell, and this is the lipid membrane all around, and COVID-19 gets attached to this ACE receptor and then enters into the lungs and infect the lungs. Well, here is the situation. It goes inside the lungs. And all these things actually, you see this is not step by step. Everything happening at the same time, even when it hits the tonsils. It goes here, and this is possibly, in my judgment, is a very, very critical stage. It's called lymphopenia. Lymphopenia means we have T cells and B cells and innate immune system. Innate immune system, they consist of mast cells, neutrophils, macrophages, and so on. They attack everybody, any antigen. Antigen means a protein which is non-self. That means it doesn't belong to the body. It's coming from outside. That is called the foreign antigen. And foreign antigen will be attacked arbitrarily, at random, by the innate system. But the B cells and the T cells, they're antigen specific. They can release, B cells releases thousands and thousands of antibodies, and T cells releases cytotoxic acids, cytotoxic proteins, and which are applicable only for that antigen, which COVID vaccines, COVID bacteria, virus, they are carrying. That means if you defeat these, lymphopenia means COVID, one way or other, completely destroys this immune system, this main part of the immune system, the T cells and the B cells. Some B cells could be little alive, and they will produce antibodies, and antibodies will be seen in a blood report, but very few. Therefore, if COVID can control these, like when cancer enters the body or cancer is produced, these are local cells becoming cancer and malignant cells. They try to control these. And you see right here, This picture, COVID does exactly the same. Almost all virus does it, but COVID does it extensively. They control the tonsils. These tonsils are the castles of T cells and B cells, especially all these are the lymphocyte, uh, lymphoid organs. These and thymus produces T cells, and they are relentless fighters. But if you can conquer this, and if you can conquer this, it is easy to go into the lungs. And you see this auxiliary nodules means the lymph nodes. They are the castles of our immune system. You see this. This is the way they communicate. Therefore, the virus COVID goes, stops this. Then what happens? The innate immune system, they are almost they are without guidance. These are the soldiers that guide them really, but they attack at random, and as they attack, they become hyperactive, and the hyperactivity causes what is called cytokine storm. Cytokine storm means there's tremendous amount of poisonous protein that these guys they will produce to destroy coronavirus. But the problem is they do not know exactly what kind of cytokine they should use, because these guys they know what kind of weapons are necessary. They do not know those weapons. They become hyperactive and they attack at random, and then this causes the cytokine storm. It means very high fever, tremendously bad inflammation, and nausea, vomiting, and finally failure of the lungs. Lungs failed, heart fails, kidney fails, and the persons die. Therefore, that is the way coronavirus works. And all these things, this is not step by step, as I said. They happen at the same time. Now, what we are doing now, we are trying to represent these ideas mathematically and see first, in using simple mathematics, what really is happening inside the body. Some people can conquer that, possibly the younger people, but the older people with weaker immune system, they cannot. I will go into a simple mathematical model right here. The very simple mathematical model, you see this, the du dt is a sub 1 u minus a sub 2 u times v. U is the viral proteins. We call the spike proteins. The viral proteins, they are increasing. The rate of increase is a sub 1. And when they are increasing, V is our, V is our immune system, and immune system will attack immediately. This A sub 2 is that chemical kinetic coefficient, we say reaction coefficient. This reaction coefficient is the reaction between U, the virus protein, and V, the cytokine, released by our immune system, and it tries to reduce U. And dV dt is, you see that this is B1U, not B1V. B1 is the rate of increase of V, which is the immune system, our defense mechanism, and B1 the rate of increase when people get sick, when we get sick, you see the doctors do a testing of our white blood count and try to see that it is increasing. It increased means if we are attacked by foreign antigens, our immune system, our number of T cells, B cells, neutrophils, macrophages, and all these dendritic cells, they will increase accordingly. And here, U is trying to defeat V. That's why this is negative B2 UV. If we solve this, I discuss in details in my book, the novel mathematical and computation studies on battling breast cancer. It is in the spring press with Springer Nature. Now we have to solve this model. You see this, first I will show you that this is I know this is very difficult to see very small letters. I could not make it bigger anymore, unfortunately. I got this directly from my computer. Now here is a picture that this is what we see. The virus is going down, that is U, is going down. This is what we want ideally. And our immune system should not go up too fast, because then if it goes up, then we have to control the immune system. It will be hyperactive, and that is cytokine storm. And see that it goes to a steady state. We want this to happen. But what happens in general, that the immune system from this state, it goes up and goes right there, which means cytokine storm has already started right here, because immune system was here, right there. You see that green? You can see this green line. Ovishek, can you see this green line in the graph? Hello? This is the green
Yes,
line.
I can see.
You can see, very good. And you see this red line? The red line goes up straight. That means the virus is conquering. Virus is strongly prevalent. And difficult for the immune system to stop it. Because why? Because the cytokine storm has already taken place, which means immune system is overactive and immune system doesn't know how to fight back. That's what is happening right here. And this is overactivity of the immune system. At the same time, the virus is increasing, the infection is going from bad to worse, and that leads to death. You look at this, here also, you see the cytokine storm, immune system was here, is going up, and the virus first goes up and then goes down. This looks nice, but because of the cytokine storm, inflammation is so strong in the body, lungs inflamed, you understand, it's difficult to breathe. Breathing is almost impossible, and possibly kidneys are failing, and body is unable to get back to normal condition because of the cytokine storm which is happening right here. And this is the situation. But there is one other case that we know, that there are some people who are asymptomatic, means they are carrying the virus. The virus is not causing any harm to them, and they have possibly mild cytokine storm, and cytokine storm is not also killing them. And that is the situation. You see this? They are going straight like that. The virus is not going too fast, means it is not increasing, and the cytokine storm is not getting any worse. It was here at the beginning, it was 7,000, it went to 22,000, although it is kind of bad, but people can tolerate that for some time, not for all the time. And this is what we call a symptomatic state. Means this guy is carrying the virus, will give the virus to somebody else, but he himself seems to be okay. How the RNA vaccine will work now? This is the question. And we have a simple mathematical model in this regard. Of course, recently I made a lot better extension, but I'll show you only the simplistic part of it so that you can understand what we are doing. You see that du dt again, this is the spike protein or the coronavirus infection, rate of increase of the coronavirus infection, the battle between the virus and the body immune system, and the vaccine is trying to control the virus. That's why it is negative. This is negative, but this is positive going on. And dVdt, this is the immune response. The immune response is increasing, is getting stronger. The more the virus is coming and affecting the body. Here the immune system is fighting back, but immune system is not fighting enough, or the storm is already there. And here comes the W, which is the RNA, mRNA vaccine, which is controlling this. And hello, can you hear me?
Yes, we can hear
Yes,
you.
Professor,
Yes.
we can hear you.
You can hear me?
Yes,
Yes,
this is Chanchal, by the way. Yeah, I can hear you.
Okay. Now, DWDT is the way the vaccine will work. We, in general, we think, or we are meant to think, that mRNA, this protein, will be injected in the body. When they are injected, what they do basically, they introduce a small amount of protein produced by the spike proteins. I mean, the small amount of spike proteins inside the body, inside the cell. And once the cells recognize that, because it is foreign, it will be recognized by the immune system, then they produce the antibodies, and T cells produce the cytotoxic acid protein, so that body knows how to fight back. When the real virus attacks, the body already knows how to fight back, because body has done it when the small amount of mRNA protein was introduced inside the cell. Now here is the situation. We think that it will work like this. We think. How it will work? We work like that there won't be any cytokine storm, which means the body immune system will go to a steady state. We do not want it to go too high, because that will be hyperactive immune system. That is bad for our body. Therefore, this will go like this, and the protein which is introduced by the mRNA vaccine, it will slowly die down. It will go and it will not affect the body anymore, and the viral infection will go away. That's how it will die. This is an ideal situation. This is what we expect. But I personally, working on this area of, working on breast cancer modeling for almost 15 years, I see that Mother Nature doesn't behave like that. I believe that
Det var
virus
liksom i
will.
mitten. Och då fick jag ju svara och liksom sen, då hade jag ju tagit ur hörlurarna och då hörde jag inte.
Any question? Hello? Can you hear me?
Det vill hon kom ju ner och föste ut mig.
Yes, hear you. I
Så
can
att,
hear
alltså,
you.
det blir inte något, det kan jag bara säga nu, att det var den bästa födelsedagspresenten som...
I cannot hear you, sir.
No, please continue. Please continue.
Let me finish, then I'll talk to you. Hello?
Yes, please continue.
Abhishek, are you there?
Yes, I am here. Please continue.
Okay.
It was an internal talk, not relevant to your talk. Yeah.
Okay. Anyway, I believe Mother Nature doesn't work like that. You know, if you look into what we say quantum biology, you will see in the micro state the medications or the fight between the medications and the infection, or the fight between the immune system and the infection do not happen just like that. The way it works, if first it goes down, then the virus will find out in a tricky way, which means through mutations. This means we are now thinking of the mutations. The mutation, they will mutate inside the body. They will mutate and try to fight back. That's why the curve is increasing. Then again, whatever RNA that we have injected, the T cells and the B cells, they know how to fight this back, because they will produce that particular kind of protein, that particular kind of you might say weapons, so that they will destroy these. As the virus mutate, our body's immune system recognize that, and they will fight accordingly, which means, as I said before, B cells can produce thousands and thousands of different kind of antibodies. Therefore, B cells will not sit silently. They will say that the previous antibodies didn't work the way it worked before. Therefore, we have to produce new antibodies, and B cell will produce new antibodies, and therefore it will go down. Then see, again, it has a tendency to go up. The B cells and the T cells, which are our relentless fighters, they will fight back again. And so in the long run, the vaccine will work and the body will be okay. This is what I believe that will be taking place inside the cell. But be sure to know, I am not a microbiologist or a biochemist. I see nature the way it works from the point of view of mathematics. Now, this is also another picture, and many of my colleagues, they appreciated this picture very much. You see what happens. The vaccine itself will not work like the way it worked right here. Vaccine itself will work a little stronger, that is a little stronger. And vaccine itself will give impetus to the body's immune system, and immune system will go like that. There is no cytokine storm anymore, and the infection will go down like this. We may try to go up a little bit, but will go down again. And this is the way it will work. And finally, what I will see, what's coming, because many of my friends ask me, how do I know that the the viral, you know, the viral uh, the viral infection will not completely go away after mRNA vaccine has been uh, used in the body. Now, here I will mention protein correction done by the mRNA. What I mean is, this is something that I hope that I'm thinking will happen in the future, which means this this is the now instead of U I used X. I just copied it from my book really. The dx dt is fx and y. X is the viral infection, and Y are the proteins produced by RNA. Now I'm thinking that RNA possibly will produce a number of different kinds of proteins to control a number of different uh, bad proteins, you might say, the poisonous proteins represented by X. And I just brought some mathematical notations here, you forgive me if you don't like them. This is how the functions must be defined. R super I, this is a real I dimensional space, and this is real J dimensional space, and they are both subspace of n-dimensional real space. Then with these chemicals, we are talking about the values, which are real values, and therefore I have to define, and they're in Banach space, because I have to take the norms of some of these values of x's and y's to understand how we can go to convergence. Convergence means the death of x and the prevalence of y. Now I may skip that, but here I want to show you this is our cell. Cell is not always very uniform. This is the nucleus in the cell, the controller, you might say. That is the DNA, and when DNA gives information, the way gene expression works, genes are here in the DNA. They give directions to RNAs, that is the transcription. RNA, mRNA, in terms, this is a very complex process, not as simple as I'm showing you. mRNA will produce the kind of proteins that is needed to make the body function properly. And these are the proteins. And these proteins, they go all over the cytoplasm right here. And then they go into our blood system and they make the body work. That is called the homeostasis. It's a dynamic equilibrium. Body is changing constantly. Your blood pressure changing, your temperature changing, but on the average, your glucose level changing, but on the average, they must come down to an equilibrium state, and that is called the dynamic equilibrium or homeostasis. If you maintain the homeostasis of the body, that means you are okay, you are not sick. Now, these equations in the element form looks like this. It's kind of bad. I do not want to explain all those things. This pi means is a product, because I'll give you an example, and that example will explain these equations. As you say, the 7.21, this is meaningless here, because I took this from my articles and from my book. That this is xi, x sub I, means there are I number, capital I number, this is the I, capital I number of proteins released by the coronavirus. They possibly will use many tactics, means many different kind of proteins they will use to conquer the body and destroy the body. And this J means, this is J right here. The J means the J number of proteins that the medications inside the cell will produce to destroy this excess. And these medications or these proteins are the Y sub J's. Now let me give you an example so that everybody can understand. Hopefully everybody can understand. I considered only two poisonous proteins released by the coronavirus, X sub 1 and X sub 2. And A1 X sub 1 means the rate of increase of X sub 1. This is the reaction coefficient between X1 and X2. X2 is another poisonous protein which will help X sub 1, and that's why it is positive. But Y1 will come is a good protein. Y1 will come to destroy X1, and that is the reaction coefficient. Y2 will come to destroy X1, and there's a reaction that will take place between Y1 and Y2. This reaction is good for the body, hopefully, because that's the way the medications have been designed. And this is my F. This is in the element form of this big F. If I can show it to you, you can see it. This is this big F right here. But anyway, and this is the X2 dt, the rate of change of the poisonous protein X sub 2, and a very similar equation. And this is Y1. This is the rate of, this is not a constant. Please see that Y1 is not a constant. I'm thinking that in the long run, some of these proteins might prevail, which will be equivalent to the normal proteins that we need inside the cells. Inside the cells, the normal proteins, which RNA in general, in a body which is not sick, which is well, in the body is produced, and they must stay on. So Y1 and Y2 must stay on. They should not go away. And they are fighting X1 and X2. You don't have to see this. This is a Charlie's convex character. This is a numerical technique that Charlie, when he worked with me at NASA Ames, way back in 1980, 81, 82. Charlie was in 82, just a 10-year-old kid. He used to work with me and enjoyed computational studies in fluid dynamics. And this is the result that you see. The result is both X1 and X2, these are the two lines, they are being controlled by Y1 and Y2. Y1 and Y2 must stay on. That's why I've got these two lines. They're not exactly the same. They may be same, they may not be same. I'm considering a general case where Y1, Y2, Y3 and all these proteins will not be exactly the same. They will change as the body changes. And that is also from that the understanding of the microstate in a cell that we do not see even when we want to through experimental studies. And here are these X1 and X2 will be destroyed, and Y1 and Y2 will prevail. And will prevail means, now you see, this is Y1 sub 0, Y2 sub 0, which means the way they are constructed in the lab. These are the synthetic proteins. They are constructed well using possibly more sophisticated technique that I can think of, and Charlie can explain it better later. These are the proteins, synthetic proteins, that we believe that AI, means artificial intelligence, will be able to guide the scientist and get this done. And these will prevail. And the next thing, I showed you uh, another graph. My time is almost over, I see, where the treatment barely failed. Sometimes treatment will fail because human bodies differ from one another. Now here you see that X, X2, which is the uh, green line, it will be destroyed. This protein is destroyed. They are going to steady state, these two, as expected, but X1, another poisonous protein, did not. It stays, it does not die. It is staying the way it was, which means that in this particular body, unfortunately, the vaccine did not work. And these are the, hopefully, and unfortunately, that 4%, 0.6% or 0.5% of the people. Now I'll go to the conclusion. Human body is not as simple as I present it. It's a very, very complicated system. One of the greatest scientists told me, who got Nobel Prize several times, his name is Linus Pauling. He told me, hardly people understand what's happening inside the body. We believe that all the scientific achievements that we have done so far barely scratched the outermost layer of Mother Nature. Mother Nature is so complicated. Now, I go back and make this statement again, that possibly one of the greatest dangers that COVID-19 causes is lymphopenia, reduction of the most efficient antigen-specific fighters, which are the lymphocytes, the T cells and the B cells. So the innate immune system, which invade all the pathogens coming from outside, they become hyperactive, and that is dangerous for the body. When COVID-19 penetrates the lipid membrane of the cell to infect with poisonous protein, mRNA could inhibit them by releasing corrective proteins. That's true. This could bring back normalcy of the body. And we have tried to model this phenomena mathematically. The second author, my son, Charlie Day, he will later, not now, he will later go much deeper with his computational techniques and mathematical understanding to see through computer simulation what more should be done to match the details of experimental data which are available. This is, of course, a very preliminary report. Thank you, and I want the very best for you.
Thank you.
I'm done.
Nice and lecture.
Okay, can I?
Yeah, maybe some questions or comments.
I cannot see you.
Okay, yes. Yes. Yeah, any question or comments, if anybody will have, please unmute yourself and ask, you can ask directly, or you can send email to Professor
Charlie, are you there? Oh, I'm sorry, Charlie cannot talk. Any question? Abhishek?
Yes, it was nice. So I will
Abhishek,
discuss
I
with you.
cannot see you now. Can I see you now?
Yeah, my is on. You can. I think you need to stop the presentation, then only you will able to see me.
How can I stop the presentation?
Yes.
I do not know. No, I
Yeah.
cannot
Can you?
stop the. Can I go back to?
Yes, you need just to put. I mean, you might have seen the cross button on the box. The box where we
So,
had arrow.
so there is a stop sharing option towards the downside of your screen.
Yes, in the
You
screen.
just
Yes,
click
it
that.
is.
Stop sharing.
Yes,
Yes,
please stop.
I did.
Yes.
Now
Now I think you can see me.
I cannot see. I can see nothing.
I think your presentation is there on the screen, maybe.
Uh, yes,
Y-
I stopped it.
yeah, you need to just maximize the screen of the meeting, the
Oh,
Microsoft
I.
Team. Yes, I think you have minimized it, or your presentation is there on the screen. That's why.
No, I do not see anything. Join the meeting. I don't see anything, but I
But
don't have to.
your camera is not on here. I think your camera is also not on, right?
My camera is not on.
We also
No
can't see.
camera is on.
Yes,
Any
we can see.
question? Abhishek,
Yeah,
any question?
yeah.
I have no
So
more.
it was a nice simulation, but yes, I will talk with you maybe later on. So we are very late today because we are
I
around
know.
50 minutes late. It was due to some connectivity problem in
That's
between we
okay.
had.
I understand that. I'm used to this.
So maybe any question, anybody else?
Oh, Professor, I have one question. This is Chanchal Pramanik. So when you showed the graph of the green color graph, so it is always linear. Whether the red color thing means for the virus, it's quite
Yeah.
non-linear. So why is that pattern so different of the virus and that of our immune system?
The thing is, you know, John, what's happening is the virus is always trying to conquer. Therefore, that the strategy that is that used for that, the strategy is that they mutate. They continuously try to mutate. Therefore, when they mutate, at that point, our immune system or even the the immune uh, acceleration which is done by the mRNA, they may not know how to do this, how to attack them back. Therefore, virus will infect further and will slowly go up. Therefore, now these guys who are going to fight, they will find out the strategy. And that strategy is already built into the RNA vaccines. The people who develop the RNA vaccines, they know, they expect these things to happen. I'm pretty sure they know. Therefore, they know this is going to happen. The RNA will adjust immediately. That's why I said that Charlie will show you in more details that adjustment, which I didn't, because I do not have that kind of computational power. Charlie will show that RNA virus is also, RNA vaccine will also adjust itself, and that must be a very slight adjustment, because every time new proteins uh, are are introduced in the body has a reaction to that. It may be that people will feel like the fever is coming back. The fever was gone, but or nausea is coming back. You understand? Some kind of pain. The people who are developing these viruses, like Moderna and Pfizer and all these guys, they know that these things are going to happen. They're prepared for that. I'm pretty sure, because very strong scientists, some of them I know, who are working on that round the clock when we sleep, they work round the clock. They know this is going to happen. Therefore, they will, subdue this 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 the system that they will put into our immune dynamics. It will make this viral going up and coming down. They will make it go down again, which means the fever will be gone, the nausea will be gone. They will be temporary, just temporary. I do not believe that that may not happen to everybody, but my experience shows that this does happen to some people, unfortunately. But that doesn't mean those people are going to die. Those people will be okay, because the vaccine will give information to the immune system. The immune system knows how to fight back. And the reason I'm sure this is done, because you see that our B cells and T cells, they do not kind only one kind of antibodies or one kind of cytotoxic proteins. Then they know how to do it, almost infinitely. They have infinite capacity. Therefore, they will find out exactly what kind of weapons they are going to use to destroy that. You understand? And therefore, I'm sure the people who are developing this, antibodies, or people who are helping the B cells and the T cells to develop antibodies and cytotoxic, the acids, the proteins. They know, they have in their mind that this will happen, and we will develop our medications in such a way that this will be tamped out, and the sick person will be okay. Got it?
Yeah. Thank you.
Yes. Yes, Abhishek Babu. Any other
Yes,
question?
thank you very much.
Any other question?
No, I don't have, because it's already very late. We are then lose many viewers as well. So I will ask you questions maybe later on. Yeah, not now.
Good.
Yes.
Good.
I have few
Feel
questions,
free.
but I will keep myself
But I request
restricted.
all these who are attending this conference, especially interested in this particular topic, to see, when our book on breast cancer techniques, battling breast cancer with novel computation studies, mathematical techniques. I wish you will study this book. This is written in a way that 99% of the mathematicians will understand.
Thank
I
you,
wrote it
surely.
for students who are kind of graduate students, or even higher undergraduate students with a good mathematical background.
Okay.
Any questions?
Good. Thank you very much. And
I'm sorry, Abhishek.
yes,
But
thank
I
you
made
very
it
much.
within my time limit. I'm pretty
No,
sure.
it's to you. It's morning now. It's for us. It's a little late, because
I don't know.
we may lose
It's
the audience then.
10:30. It's not that late. It's
Yes,
about 10:30. People
yes.
think
This
tea.
meeting is going on till 6 hours, around 7 hours. It's
I'm
almost.
sorry.
It's
Abhishek, I'm sorry. I understand. You're
yes.
tired.
So yes. So now may I request Kalsup to please be ready, because it's now your turn. So Mr. Kalsup is an engineer. So he is interested on mathematical physics, especially on color research. He has founded a color research center in US. And coincidentally, we had the consecutive three speakers who are at some point of time, all of them were associated with NASA. So Carl has also some association with NASA. So without having any delay, it's my great pleasure to welcome Carl Su. So Carl is now yours.
Okay, can you hear me okay?
Yes, we can hear you properly. Yes, we can see you as well. So now we need
Okay.
to see your screen. That's all. Yes, great job. Yeah. So now it's your screen on your screen. Yeah, it's your whole screen. Yes, in one go. Great. Now your
Okay.
presentation. Yes, great. Okay, thank you.
I'm good to go? All
Yes,
right.
please. Yes.
Bit of a lead in with what I'm doing is a follow-up from a paper that I had done last year where I had proposed that a decoding of an ancient symbol could be done with audible sound. And that I ran into a few complications in doing that conversion. And my paper that I submitted has the solution to it. But what I found that I had to do was to develop a infrastructure or a foundation for the mathematics that I was, working with. So converting something from visible light to the range of audible sound was the challenge. What the way things turned out. So what my planned approach is going to be is, per this outline that I've done. So I first want to introduce you to some of the concepts, some of the interpretations of geometry that was done. And so I will introduce you to my submitted paper. I will go into the additional research that I did, and then I'll touch on the lecture version of my paper. So with the submitted paper, I'm going to talk about the ancient portal thought experiment that was done. Attachment A was doing the presentation using visible light, and visible light has its particular problems. And attachment B was repeating that thought experiment using sound. And kind of a spoiler, yes, things in the range of sound will work. So, but whether or not sound itself will work, I can't say that specifically. But the issue was, could I model color in the range of audible sound? And that's what the yes is about. Uh, Coupling is the sharing of energy, and that there's been some research done in regards to something that's called X point. This was done by a researcher from the University of Iowa, I believe, a gentleman by the name of Jack Scudder, and that he showed where the interaction between the Earth's magnetic field and the sun's magnetic field created what appeared to be portals in space. So I want to explain a little bit about the geometry in regards to the hexagram and Metatron's cube. I will identify the significance of the total range regarding the color hexagram. That's where I had experienced problems. The additional research identifies a correlation between visible light and audible sound. A major problem that I had was when I color modeled in the range of visible light, there was only one color model there. And when I start color modeling in the range of audible sound, I found 14 subharmonics within the range of audible sound, and it confused me. But the solution that I came up with had to address ultrasound, audible sound, infrasound, and the electromagnetic frequencies as well. So sound waves are mechanical waves, electromagnetic frequencies is radiation. And so whatever solution that came out had to address all of these areas. I use harmonics and subharmonics, and I developed tables to show this. So I'll probably just skip over a lot of the wording that I have and move on to the tables because it's easier to see what I'm talking about when you're looking at the table. I'm also looking at the possibility of using the conversion methods that I've come up with in terms of bit mapping, to where if you're looking at something in another frequency range other than visible light, you can convert it back to visible light, so that if you have like a satellite that's looking at something in the ultraviolet spectrum or infrared or X-ray, that this would allow you to convert it back to a visible light image versus using false colors. And I'm also taking a stab at the type of color resolution that you could expect, with conversions back to visible light from other spectrums. So what happened to me allowed me to grow the color concept, and that as panicked as I was in trying to figure things out, it worked out for the best in the long run. So when I get to the lecture version of my paper, that you'll see that the chapters or the parts are from a book that I'm putting together. It's the second book. And I'll introduce you to some of the geometry correlations in regards to Metatron's cube. Then in terms of color modeling, I've come up or identified some shortcuts, and that I reverse engineered what I had done in audible sound back to visible light as a check to make sure that, okay, everything's still working. And again, bit mapping, harmonics from one area back to visible light, and to also just give you a heads up as to where this research is going, is that if I can do audible sound, then this translates over to the circle of fifths as well, and that will tie it into actual musical tones. So this is just an introduction. It's just something that for each chapter in the book that you have to have some opening statements. So this is my paper. This research has predicted that color is applicable to the entire electromagnetic spectrum, not just the visible light spectrum. Therefore, the concept of color and the associated color mechanics are scalable. The frequencies of sound, mechanical waves, are also they also exist as electromagnetic frequencies or radiation. A defined audible sound color model would make it possible to convert the visible light version of Metatron's cube decoding to audible sound. This would be an alternative method of creating a subspace opening or a portal per color theory, basic color mechanics 4.0, an ancient portal, thought experiment, attachment B. So the conversion method that I applied used the exponential equation formula, and my primary red reference is at 450 terahertz. And I'm using the 55th subharmonic of this equation to come up with my referenced primary red in the area of audible sound. The range of audible sound, which is a international standard, is from 20 to 20,000 hertz. And that what I ended up using was basically about a 20th of that range. And that where I had used the 450 value to determine the subharmonic, I used the same approach with the total range for that I had associated with visible light to get this particular subharmonic value. So this is just breaking everything down in terms of important relationships, a 1/12 value, a 1/6 value, and I can throw numbers at you, but I think I can get my point across quicker when I can show you the geometry. So the hexagram has 6 points, and that it has 6 interface points as well, and that's where the 12 comes in. And this is one of the first tables that I had come up with so that you can find the different reference points, whereas you have to establish what the system level 0 is. And once you find what the system level 0 is, then you're just adding 12ths to that base value to get the other primary colors, and that there's a relationship of consecutive odd numbers that will give you the values of the primary colors, and that consecutive even numbers will give you the value of the interfaces between the primary colors. And one of the things that I've established was a new set of circular constants. And so this is the circular constant that's associated with the primary red. And that these values go in a pattern to where when you combine any two, you get the value of the third one. You can get into that a little bit later. Things that share energy or coupling, this happens with the 4 fundamental forces of nature. The forces are the strong nuclear forces, the weak nuclear forces, gravitational force, and electromagnetic force. So when I'm talking about radiation and electromagnetic spectrum, visible light, it's the electromagnetic spectrum or the electromagnetic force. Strong and weak nuclear forces are regarding atomic structures. Gravitational electromagnetic forces can have an infinite range. When frequencies are harmonics or subharmonics of each other, coupling happens more readily. An example of coupling is in the work of Jack Scudder, a plasma physicist at the University of Iowa and a NASA researcher. He's researching what is called X points. These are places where the Earth's magnetic sphere and the sun's magnetic sphere interact to form what appears to be portals. This interaction takes place in the vacuum of space by similarity to the electromagnetic force. This color research has included sound wave frequencies as well. And that ties in with the value that I picked here in regards to 1,441 hertz. That's in the range of magnetism. So in talking about the magnetosphere, it's just the interaction of the magnetic field of the Earth with the magnetic field of the sun. In explaining color or working with color, I've worked out a hexagram relationship. And that what this is talking about is I developed a basic 1, 2, 3 color model, and realizing that when you're talking about color, when you reference it and you look at a spectral spread of color, it tends to kind of like imply that you would have red, green, and blue, and this happens sequentially. And in fact, it happens at the same time. Everything is cycling at the same time. And that that red, green, and blue, I formed it into an equilateral triangle. And in addition to that, if you flipped everything 180 degrees out of phase, you would get a cyan, magenta, and yellow equilateral triangle. And the combination of the two color systems will give you your 6-point hexagram diagram. And if you were to name things from lowest frequency to high frequency, you would have your red, yellow, green, cyan, blue, and typically it's magenta. So, but for what I'm using this for right now, violet. Violet and magenta can be swapped out. Violet is the equal combination of red and blue to give you magenta. But I'm looking at this more in terms of a spectrum chart display, and that this is the high end value. And also this is the location of my zero as well. So my primary red is here. I have my 6 reference points. I have my 6 interfaces here. And so in determining my system level 0 for my color system, that I subtract 1/12 of the value from my primary red, which give me my 0 right here actually. So this is the violet value, and its second half comes here. A primary color sits in the very center of its range, and its range is 1/6 of the total range value of that particular defined color model. And so 1/6 or 1/12 of the range of this primary color is above, and 1/12 is below, giving it a range of 1/6. And so my colors are defined by numbers and geometry versus what you see visually. And so these colors will not be the most yellow or the most green or the most blue, but with them being listed in the way that I have them, that when you look at the layout of the colors, that it forms your red, green, and blue triangle, and your cyan, magenta, and yellow triangles. And what this also identifies is the circular constants that I'm using. These circular constants use a different time base. So if 1 second was defined as being 60 divided by 60, that these circular constants would use a time base of 61 divided by 60. I refer to it as being the long second. And that these circular constants, which are negative and positive, are part of a family of new circular constants that I call the 10x family of circular constants, where x is not equal to 0 and x goes to positive and negative infinity. And that red is represented by 10 times positive little phi. Cyan is represented by 10 times negative little phi. And this gives you your value for yellow. 10 times plus or minus 1 gives you the value for green and your violet, or magenta, however it comes out. And 10 plus or minus a big phi gives you your yellow, with yellow being 10 times negative big phi, and blue being 10 times plus big phi. What that gives you in terms of unit circles is that 10 plus or minus little phi is a circle in the center, being of the same diameter. You only get one circle. The same thing for green and violet is that it's represented by a larger circle that's proportional to the other two circles. And your yellow and blue is again same diameter, which from my research, you're looking down the x-axis, which is at the very center here. And that would imply that if I'm looking at circles and I'm looking at two events that are happening at the same time, occupying the same space, that I'm not looking at a sine wave. I'm looking at a helix. And I got a helix or three pair of helix that are 180 degrees out of phase with each other and cycle in such a way that they're occupying the empty space of the other helix. And another way of expressing this interaction is with 6 separate circles where each circle represents a primary color. So that's what's going on. And the problem that I had dealt with the total range, and the total range would allow you to go from one point of a circle through the center to the most complementary color on the other side of the circle. And if the total range is inaccurate, if it's too large, then when you come through the center of the circle, that the most complementary color is going to be to the right. If the total range is too small, it'll be off to the left. And this is Metatron's cube, and that this is made up of 2 cubes, the larger one on the outside, the smaller one in the inside. And the question that came up is, in what does these lines represent? I had looked at them as being nodes of some type that communicated to one another, but the answer could simply be that this is magnetism, and that what is happening is that it's being shared throughout the system and another system, and that this other system is this smaller cube here, that per the color hexagram geometry, that using that as a decoding device, these 2 cubes are the same size, and with the x-axis being equal to 0, and if my time axis is also equal to 0, then the cube space itself becomes 2-dimensional. So that is the basic paper. This is me getting into the research that's talking about the problems that I had, and that there was 14 subharmonics, and that of the visible light color model, and what I needed to do to solve the problem. These are just other names for possibly wormholes or portals. And this gets into the first table that I had developed in regards to how I solved the problem. So this is my baseline. This is for visible light. I did the calculations 10 above the area of my baseline. So going up at the area of X-rays and cosmic rays, and using the harmonics. And so the correlation here is little phi can also be represented by phi raised to the -1 power, and big phi can be represented by little phi raised to the -1 power. They're the inverse of each other. So I'm keeping track of my exponents here and going through my system. And this is where I realized that I had 14 subharmonics of the primary red anchor. My baseline values, and I had to come up with a way to resolve this. Every one of these subharmonics could not have a total range of 20 to 20,000 hertz. It just didn't make sense. So it raised the flag. This is the one that I have at the 55th subharmonic. And have a note here, gravitational waves. This is a reference from Wikipedia. Stephen Hawking and Werner Israel list different frequency bands for gravitational waves that could plausibly be detected, ranging from 10 to the minus 7th hertz to 10 to the 11th hertz. So I quit doing subharmonics when my values started to come out to be negative, but apparently I could have or should have kept going. The solution for the total range problem that I had was, again, I just used the total range as my value that I was taking subharmonics of. The result is that when I now look at my baseline value, that I have straight across from it a total range value that ideally will allow me to get my hexagram geometry done right so that I can go from one point on a circle through the center in a straight line to identify the complementary color. And only one color model is identified here. Above visible light is ultraviolet light. Below visible light is infrared light. When I got down to the 55th subharmonic, what I'm looking at is that it's magnetism. And the correlation to magnetism here was done per the Earth's electromagnetic field, in that near the area of the equator, that the Earth's magnetic field is about 1,300 hertz. And in the middle latitudes, it's about 2,000 hertz. And near the poles, it's about 2,500 hertz. So this is showing something where there's multiple color models of the same electromagnetic phenomena within the range of audible sound. So whether or not a theoretical portal could be used it being activated or enabled with audible sound, or frequencies within the electromagnetic spectrum, this I can't say it answers the question, but it answers the problem that I had with how would you enable something to share energy, to couple. And when you're in these lower frequencies in the electromagnetic spectrum, they naturally have the transformer action going on. You have these fields of radiation that are interacting with one another. So that, just getting down to audible sound and doing color modeling, that I learned a lot more in regards to, okay, audible sound is one thing. You're going to have ultrasound above here, and it goes up to about 2 or 4 megahertz, and that in the range of infrasound, and those are the frequencies that are below 20 hertz, that I identified approximately 16 subharmonics. So again, is talking about what's going on with the math and what's going on with electromagnetic radiation, or the electromagnetic spectrum. And if frequencies are frequencies, then the same thing would apply. And depending on where you live, your electricity is at 50 hertz or 60 hertz. And so again, something is falling out in regards to electricity, which is matching up with things that we see in the real world, and therefore it encourages me in that my solution, taking this route, is probably more feasible than trying to color model all of audible sound as one color model, which, looking at it just doesn't add up. A better solution, when you divide the total range, well, the primary red anchor divided by the total range, you get a value of 1.5. When you divide, which is, you're talking about a harmonic now. When you divide the total range by the primary red anchor, you come out with a value that's basically 2/3. And me just arguing with myself, that using the value 2/3 is a good approximation, that you don't see a difference in values until you get out to about the 10th decimal point. And therefore, if you have a primary red anchor and you multiply it by 2/3, you'll get the total range. And that's what I have here. So this is something that you wouldn't have to go back and redo. But when I was first trying to work this out, I was trying to make all these calculations. But if my reference is close, then these values, total ranges, will also be close. So one other thing I did was that I took a look at the total range value where I had used 300 terahertz. I went to 360 terahertz, which is out of the outer edge of being acceptable in terms of the total range of the visible light spectrum. And it turned out that at the 55th subharmonic, the difference was like 200 hertz. So it's like adding 33 hertz to each, to the range of each primary color, which again is saying that, okay, I'm on the low end of what the total range is. And if I look at the excessively high end, and if the difference is only at, 200 hertz, that it puts me pretty close to where I need to be. And this is, in the last few minutes I have, some of the geometry. This is just talking about space. You have the color hexagram that I worked. I'm looking at, okay, is there a correlation between these two geometries? And that I needed a third geometry in order to prove the orientation, not that their intentional use, original use were the same, but did the geometry correlate? And from the color hexagram geometry, I know my x-axis is in the very center, and that with this geometry, that it relates to what is called Metatron's cube, and the cube is described with only 6 corners being shown. But knowing the geometry of the hexagram, and the 3-dimensional version of the hexagram is the star tetrahedron. So I would have a corner here and a corner behind me, and a star tetrahedron, if you looked at it, it's a cube. It's just a cube with cutouts. And so this is the orientation of a star tetrahedron with the corners along the x-axis. The front top corner is in line with the rear bottom corner. And when you end up going through this geometry, looking at everything, and going to Metatron's cube, to me, it shows that, okay, the correlation is right. And if the electromagnetic radiation from magnetism is what's being depicted here, and what approach I took to this was that I was looking at a schematic, an engineering schematic, uh, engineering drawing, and my interpretation of what was going on was from an engineering aspect versus uh, something that I just, believed in. And when I looked at it as far as being a um schematic and that these nodes were some type of computer network, I had looked at, okay, is there a cycling pattern? So these numbers actually just represent me thinking, okay, I go 1, 2, 3, 4, 5, 6, 7, 8, and that this thing just cycled back and forth, sharing information or whatever. But I can now look at this and say, possibly this is just an indication that certain magnetic radiation is being shared, and possibly this actually making like a magnetic lens or a magnetic prism that causes uh, a opening in space time. So a subspace opening of one sort, and with two subspace openings connecting to one another, and with the x-axis being 0, my time axis being 0, would I have anything less than two spatially separated locations being connected by a two-dimensional plane? These are just shortcut methods. This is me reverse engineering what I had done back to visible light. And what I wanted to talk about in the last few minutes that I have is that using my primary red anchor, I got 300 terahertz divided by the 400, at 300 terahertz from my total range divided by the 450 terahertz of my primary red anchor, which gives me a fraction of 2/3. If you were to look at making a correlation between another harmonic or subharmonic, it would just be a matter of replacing these values, which with them being harmonics and subharmonics, that they would have a relationship of 2 divided by 3. And therefore, if you wanted to find out what the value of your 0 is for another harmonic or subharmonic, you would just put the total red anchor value here, the total range value here. I'm saying that wrong. You would replace the total range value here and divide the total range value by this fraction, and it will give you the frequency for that particular color model or harmonic or subharmonic, and you would get a quick reference of 12 reference points within that particular color model. So I believe I'm about out of time, and I'd love to read my summary for you. But what I'll do is just highlight. You can see on my paper, this is my website. If you're interested in my material, these papers are listed on my website. It will take you back to the earlier proceedings of this math conference, and that you can read more about my circular constants and the other things that I have going in regards to this. Next year is going to be the circle of fifths. And thank you.
Thank you, Carl, for your colorful talk. And certainly we'll have again tomorrow on the same topic, but of course in a different way that he is going to talk about. So any question or comments if you have? If you have any question or comments, you are welcome to, you can ask him directly. Okay, if not, then thanks once again. And thank you very much, Carl, for your nice talk. And
Thank you.
timely completed it in exactly the same time that is required. And tomorrow the same link will also do. Okay.
Same
The same
link?
link that, yes, same link. So I think you missed my earlier email. That's why some confusion came. So the WhatsApp, not WhatsApp, this YouTube link is basically for the other participants. So like we shared the link to mostly to the participants, and those who are viewers are actually seeing this whole event using YouTube. So we have plenty of YouTube viewers. So around yesterday it was around 750. So I'm not sure how many of them are today also there. So let's see at the end of this session when we stop the YouTube link, then it will give us the exact count maybe.
Awesome.
Okay,
Congratulations.
so yeah, so nice to see you again virtually. Thank you very much. So that's the end of this whole session. It's quite long, and I can see my watch, the meeting watch. It says that 7 hours 42 minutes and 36 seconds now. 7 hours 42 minutes 39 seconds now. So it's a long
Wow.
day. Yes, and all the team members are working very hard to make it a live streaming and all. So people are sitting at different places, but they are doing it nice job. So thank you to all of you, and good night from India Standard Time. Okay, so then see you tomorrow again virtually.
See you
Okay,
tomorrow.
bye. See you
Thank you.
tomorrow. Bye. So Jandan, please stop the stream.